All right, shall we begin?
Yeah, let's welcome our first speaker, Prantik Chatterjee from IIT Kanpur. I'll let him introduce the work that will appear in FMCAT this year. Take it away, Prantik.
Hello, everyone. So I'll be presenting my work on Hydra, a framework for distributed program verification. So this work was done in collaboration with Professor Shubhajit Roy from Department of Computer Science and Engineering, IIT Kanpur, Wei-Fei Deep from Department of Information Technology, Uppsala University, Sweden, and Dr. Akash Lal from Microsoft Research, India. This paper is scheduled to appear in FMCAT 2020. So the problem we are working on is program verification. So given a program P and a specification R, we are interested to know whether there exists any execution of P that violates R. If yes, then we say that P is unsafe with respect to R. Otherwise, we say that P is safe. Now, verification tasks are computationally intensive. They are very resource hungry. And these days, we have large computational resources available. Now the question is, can we make use of these large computational resources and distribute a verification task across multiple machines? Now, one of the popular approaches for doing program verification is symbolic model checking. So in this approach, given a program,
Looks like we lost our speaker.
Yes.
hello.
Yep.
So you
Should
can
we?
see, right? See my
Should
screen,
everybody
right?
else kill their video just to avoid
Yeah.
taxing the bandwidth?
Hey, Prantik.
Hi, you guys can see my screen, right?
Yes.
Yes.
Oh, okay. So let me continue. So given this verification condition, now we feed this to an SMT solver. So the job of an SMT solver to check for satisfiability. So if it is unsatisfiable, then we can say that the program is program is safe with respect to the given specification. And if it is satisfiable, then we can say that the program is unsafe. Now, often we do not want to explore all the program paths, but rather evaluate only a subset of the program paths. So this means we only unfold the call graph of the program unto a certain bound. So this approach is called bounded model checking. And one of the popular algorithms which does this bounded model checking is called stratified inlining. So stratified inlining, given an input program P with a starting procedure main, it can say whether the program P is safe or unsafe. If it is unsafe, then it returns an execution trace on which the program P is unsafe. So consider the example given. So in this program P, the main procedure modifies 3 integer variables x, y, z and a Boolean variable c. Now main has 5 basic blocks. From L0 you can non-deterministically jump to L1 or L2. In L1 we assume c is true, then call foo and x on x and z, and then we can go to L3. Or in L2 we can assume that c is false, call bar on x and z, and then go to L3. In L3 we call buzz on y and then go to L4, and finally in L4 we check for an assertion violation on z. Now these function calls in this block L1 and L2, these are called call sites. Now initially when we begin, we put all the call sites on main into a set called C. Now we iteratively do the following. So at first we construct an abstraction of the program by under approximating all the call sites in C. So this means we block all execution traces through all call sites in C. Now we can we check for satisfiability on 5 with a SMT solver. Now under approximation, since we have already blocked all the executions through C, this represents a subset of the program behavior. And if it is found to be satisfiable, then we can safely say that the program is unsafe. Otherwise, we construct another abstraction of the program by over approximating the call sites. So in the over approximation phase, we can say that all the call sites are open, so execution traces can go through any of them. Then again, we check for satisfiability on psi. Now this psi represents a superset of the program behavior, and if it is found to be safe, then the program is definitely safe. Otherwise, if we find an execution trace which is unsafe, then we can define the abstraction of the program by inlining all call site C prime which exists on the execution trace T. Then we can remove these call sites from C and then include all its children call sites into C. In this way, we can check the safety of a program. So Codal is a popular tool which implements this stratified inlining algorithm. So Codal is used by Microsoft Static Driver Verifier. It's a popular tool, state-of-the-art verifier. Now, when we define the abstraction of the program, consider from this example. So inside main, you can either, if C is true, you can go to foo, then buzz, and then check for assertion violation. Else you can go to bar and then buzz and then check for assertion violation. So if in the over approximation phase, you can find an execution trace which can go through foo, then buzz, and then check for an assertion violation. So in this case, you will end up inlining foo and buzz from inside main. So you can construct a tree, so where main is the parent of foo and buzz, and then you will probably inline the children call sites of foo and buzz as well. And if you find this part to be safe, then we will again refine the abstraction of the program by inlining buzz and all its children call sites. Now the question is, can we split these verification tasks? So consider this scenario. When you have inlined foo and buzz from inside main, you construct two partitions from this program, from this state. So in the left partition, you say must reach foo. So in this part, we will consider only those execution traces which must pass through foo. And on the right partition, we say must avoid foo. So in this part, we will only consider those execution traces which never pass through foo. So in the left part, we will inline foo, buzz, and all its children. And in the right part, we will inline bar, buzz, and all its children. Now you can verify this must reach foo and must avoid foo in parallel. If any of these partitions are determined to be unsafe, then the entire program is unsafe. And if both of these found to be safe, then the program could be considered safe. Now, of course, we do not need to split the program only 2 times. These must reach foo and must avoid foo parts can again be split to increase parallelism. Now the question is, which call site should we split on? Is that an example where from inside main we can call buzz on some variable buzz which has a variable z, and then we can check an assertion violation on z. Otherwise, from main we can go to foo, modifies variable x, then go to buzz, and then check for assertion violation on z. Now, if I try to split on foo, what happens is the must avoid part. In the avoid part, you will end up inlining buzz, all its children, and in the must reach part, you will probably not need to inline any children of foo at all, because none of foo or neither foo nor its children provides these assertion. In this case, both must reach foo and must avoid foo. Both of these.
We lost him again.
Hey, so by the way, hi, this is Akash. So I'm one of the co-authors on this paper. If you have any questions so far, I can answer them while we wait for Prantik to come back and join.
Hello.
Oh, there he is.
Hello.
Go ahead.
Okay, so if modifies both of these partitions will evaluate different proofs. So clearly the decision to which call site to split on is important. Now,
Antik, could I interrupt you for a sec?
yeah, sure.
Yes. Could you just go over that slide again? Because even before your connection cut out, it was kind of tenuous, and I'm not sure people understood the example.
Okay. So consider this example where from inside main, you can go to buzz, which modifies a variable z, and then you can check an assertion violation on z. Or you can, from main, you can go to foo, which modifies x, then go to buzz, and then check for assertion violation. Now consider what would happen if we decide to split on foo. In the must avoid foo part, you will go from main to buzz and then inline all the childrens of buzz and then verify that part of the program. And in the must reach foo part, you will probably not need to inline any children of foo at all because neither foo nor its children modifies z. So both the must reach and must avoid parts will be exploring the same proofs of the program. But on the other hand, if foo did modify z, then the must reach foo part and the must avoid foo part, those partitions will be exploring different proofs of the program. So the choice of call site is clearly important. Now, to decide which call site to split on, we use the minimal unset code. So remember in Codal, we alternatively fire an under approximation query, then an over approximation query. So when we fire an under approximation query, we extract the minimal unset code. So given an unsatisfiable formula phi expressed as a conjunction of clauses phi1, phi2 up to phi n, a minimal unset code is a subset of clauses psi which belongs to phi such that whose conjunction is still unsatisfiable and every proper subset of psi is satisfiable. Now our intuition behind designing this splitting heuristic is that when we find that some inline call sites are not part of the minimal unset code, we can consider them to be search irrelevant because clearly whether or not they were inline is irrelevant to conclude the safety of the program at this particular point. So we decide to design our splitting heuristic by considering to split on any on a call site which appears on the unset code. Now we implemented our splitting algorithm on a tool called Hydra. So the architecture of Hydra looks like this. So we have a server node and then we have multiple client nodes. So when we want to verify a program, the server sends the program to client 1 and client 1 starts verifying the program while client 2, client 3, etc. these guys sitting idle. Now when at some point client 1 decides to split on some call site C, it constructs two partitions, must avoid C and must reach C. So it continues verifying the must avoid C part and sends the must reach C part to the server, which the server enqueues in its own queue. Now, when some client is idle, the server can dequeue this task and send this task to the idle client. So now client 1 and client 2 are both working parallelly on the must avoid C and must reach C part. Now, what are these partitions that we are talking about? Because I am explaining this because we need to understand partitions to know how to deal with concurrency overheads. So consider this scenario where client I is working on some partitions. So it has inlined some call sites A, B, and C, and then it decides to split on B. So now it's working on the must avoid B part while it sends the must reach B part to the server. And at the same point of time, client J is also working on some other partition where it has inlined X, Y, Z, these call sites. And then the client J finds that these partitions that it was working on, it has been verified. So then client J requests a partition from the server. Now, before the server can send these partitions to the client J has to reset its own prover stack. And after resetting this prover stack, the client J, before continuing verification, it has to initialize its own prover before continuing verification on the must reach B part. So essentially, it needs to first inline A, B, C, push the must reach B decision to its own prover, and then only it can continue verification. Now this initialization part, this incurs an overhead. So to deal with concurrency overheads, we have to basically deal with challenges. The first one is we want to reduce this initialization overhead, which we try to solve with a double-ended work list. The second is we want to balance load across multiple clients so that we don't want that one client is doing all the work while other clients are sitting idle. And the third is we also want to control degree of parallelism, because consider that we have only 2 clients available. So then it doesn't make sense to do, let's say, 10,000 splits, because then all the clients will be doing is incurring this initialization overhead rather than verifying the actual program. And on the other hand, if you have, let's say, 100 clients available, you don't want to do 10 splits or 50 splits, because then most of the clients will be sitting idle. So to control this degree of parallelism, we implement feedback directed splitting. Now to solve this initialization overhead, we do the following. So for the server maintains a single queue for each of these clients. Now, whenever a client wants to push a partition, let's say client I is in this state, it has inlined some call sites A, B, C, then it decides to split on B. So it's working on the must avoid B part. Then it inlines D, E, etc. and it's continuing. And it sends the must reach B part to its own queue in the server. Now, when it sends this partition must reach B part to the server, it pushes to the left of the queue. Now, note that if you always push to the left of, if a client always pushes work to the left of the queue, so the rightmost part of the queue will contain those partitions which will incur the least initialization overhead, because in those parts lesser call sites are inlined and lesser split decisions are there, while the rightmost parts will incur the heaviest initialization overhead. So if client I has finished verification in this part, in the must avoid B part, then what it can simply do is it can pop the leftmost partition from its own queue from the server, pop the inline D and inline E part, and flip the last split decision. So must avoid B, so it pops inline D and inline E, and then simply flips the decision. So it's now working on the must reach B part, and it continues verification. Now, when another client J, it has completed its own work, it comes requesting a partition from the server, and if the queue for client J is empty, then it steals work from another client. So which client should it steal from? So whichever client has the most pending work remaining. So the server picks the client which has the largest queue and then pops a partition from the right, so that client J will incur the least initialization overhead. And finally, to control the degree of splitting, we have implemented a feedback directed splitting heuristic. So when we want to split, we can simply check whether the Unset code contains any call site to split on or not. So along with this, we also add another criteria. So you check, so we have a variable delta. So whenever delta time has passed since the last split, only then you can split. So initially this delta is set to a small value, which is delta C. This is our initial split interval. And then we have another 2 variables to consider, which is QI. QI is the work queue of client I in the server, and WT is the currently queue which contains the currently idle clients. So now the new split interval should be high if the ith client has a lot of work remaining in its own queue, and there are a lesser number of idle clients waiting. While the delta I, it should be lower if it has less amount of work in its own queue and a lot of clients are waiting. And if no clients are waiting, then we simply increase this delta C by multiplying it with a large constant. So delta C and K, these are all determined empirically by doing experiments. So our experimental setup is like this. We perform all our experiments on static driver verifier benchmarks. So these are benchmarks which exercise all features of the C language, and these are real life Windows device driver benchmarks. So from these benchmarks, we select only hard benchmarks, so which are hard for Codal to solve. So by hard, I mean that we only choose those benchmarks on which Codal takes more than 200 seconds to solve or it times out. So we set the timeout value to 1 hour. So whenever we are comparing Codal and Hydra, we try to verify programs within 1 hour. And then we ran Hydra with 32 clients on these hard benchmarks and finally compared the verification time of Hydra with that of Codal. We have also validated our strategies for dealing with these concurrency overheads. So we performed an experiment where Hydra has a random splitting heuristic. So it can pick any call sites randomly and then split on. So we ran this algorithm 5 times on hard benchmarks, and then we check whether this performs any better than the Unset core-based splitting heuristic. So we saw that the Unset core-based splitting heuristic, this performs statistically better than the random splitting heuristic. And we also saw that the double-ended queue-based work stealing, this performs statistically better than a classical work stealing algorithm. And the feedback directed splitting also performs statistically better if we didn't control the split rate. Now, these are some experimental results where we compared the number of solved instances within 1 hour by both Codal and Hydra. So out of all the hard benchmarks, we saw that 41% instances
Randy, can I
neither
interrupt you?
Codal nor Hydra could solve. Yeah, sure.
So this works. You didn't mention what machine did you use for comparison? Was it like a cluster where you run things distributedly and a single machine, or?
So we had one machine for a server node. So it had 16 cores and 64 GB of RAM. And for the client nodes, we used another machine which contained 72 cores and 144 GB of RAM. So note that clients do not communicate with each other. So since we are running servers and client nodes all on different machines, so the communication overheads are already taken care of. So essentially, if you yeah, sorry.
So your architecture is a big multi-core machine, as opposed to say a cluster or cloud.
No, you can also run clients on multiple machines. So you can have one server node and then you can distribute these clients on say 8 machines or 10 machines.
Right. But for experiments, it's just beefy machine and you're using the many cores.
Yeah, right.
Oh,
But
okay.
again, note that, yeah, okay. So so there were only 4% instances which Codal could solve, but Hydra could not. And then there were 25% instances which both Codal and Hydra solved. And finally, there were 30% instances on which Codal timed out, but Hydra solved within 1 hour. So overall, Codal solved 29% of the hard instances, whereas Hydra solved 55% of the hard instances. Now, this is another result which shows the comparison between running time between Codal and Hydra. So I have plotted the time taken by Codal on hard instances in x-axis and time taken by Hydra on y-axis. So in most cases, you can see that Hydra takes significantly lesser time than Codal. Now here I have plotted the speed up that Hydra gets over Codal when you take it on only those instances which both Codal and Hydra could solve. So in most cases, Hydra gets 5 to 10x or 10 to 30 times speed up over Codal, and on average it gets it on approximately 20 times speed up when you use 32 clients with Hydra. So we also performed an experiment to check the scalability of Hydra. So as you increase the number of clients, how does Hydra's performance change? So we performed experiments with Hydra with 1, 2, 4, 8, 16, and 32 clients respectively. So you can see the number of instances solved within certain time in x-axis. So as you can see, as you increase the number of clients, the number of instances solved also increases. So to conclude, we developed a verification engine called Hydra that can distribute a bounded model checking task across multiple machines. And our experiments show that Hydra is significantly faster than Codal. Hydra is open source and available at the Hydra branch of the Codal repository. And a preprint of our paper is also available at the following link. Thank you. So if there are any questions.
Excellent. Thank you, Partitioning. Applause is decidedly awkward over Slack and Zoom. Yeah, so I have a bunch of questions, but let's open it up to the audience first.
Steven, I think, oh, you're clapping. I don't think that's the raised hand.
Maybe I'll start with a question then. So kind of, you've compared against Codal, but I was wondering maybe for, if you could speculate, I know empirically this would probably be very hard to compare, but you're doing kind of, your notion of modularity is somehow modular across different kinds of paths. A normal, usual notion of modularity in verification is at the, method or procedure boundaries, like computing procedure summary, stuff like that. I wonder if you could speculate on, what would be how would you compare the two in terms of what they can and can't do?
Yeah, so when we parallelize, it's in terms of the VC. So whenever you generate a VC, you essentially, when you do this split, you are splitting the VC into partitions. And so, yeah, so sorry. So yeah, what were you asking? Sorry.
I'm just thinking like, another way of splitting might have been, instead of splitting per path, just when you get to a procedure, just ask, I have no idea how this works, I'm just speculating. Just ask, I have a entry point and an exit point, and see if there's a feasible path between those 2 points. Like, splitting, based on offloading the computation of procedure summaries rather than offloading the computation of alternate paths. I think these are two different things, very hard to compare, but I wonder if you might have any speculation on how these two approaches would compare.
So I can add something here. So,
Please.
our strategy so far has been, so this is disjunctive splitting, meaning that in any partition, if you find a bug, you're done. And this was done with the purpose that we wanted to find, the real value of bounded model checking is in finding bugs. So that's what we were targeting. So in that sense, this is specific for that case. It wasn't designed for. I think you will need a slightly different algorithm if you are going to be computing procedure summaries. You don't want disjunctive splitting in that case.
I could imagine like, trying to do under approximate procedure summaries or something like this.
Right.
For bounded model checking.
I'll ask a question. Do you have a feeling how good the splitting strategy is itself? Because if it's just searching for counterexamples, then by doing this in parallel, you're also changing the search heuristic. And is the search heuristic more effective as well? Or is it just because you do things in parallel?
What do you mean by a search heuristic?
Well, you guide the search to a particular kind of bugs. Like you'd say, I only want counterexamples that go through a function, only that don't go through a function. If you generate a monolithic VC, you let the SAT solver do those choices, but at a much lower level, and so it doesn't have the same high-level ideas of where to split. So if you just take the individual SAT queries or SMT queries that are generated by Hydra and sum that up, is that faster than the monolithic one or not?
Prantik, can you go back to your scatter plot?
Right.
So the monolithic one is certainly faster in some cases, even with parallelism. So sometimes, yeah, you have to let the theorem prover do its job. But where Hydra works is when it gets too big. When you start exhausting memory on your system, or the formula is just getting too big, that's when the parallelization starts to kick in.
Right, that's what I'm thinking, that maybe that's when the split starts kicking in, not just parallelization. Like maybe Hydra is good even when you have just one core. But
so that's the cactus plot. Can you go to the cactus plot? So with one core, it's
Right.
the next one, right?
This one.
With
So
one core, it's actually a little bit
Hydra
worse.
with one client. Yeah.
It's a little bit worse. So yeah, so we should not do the splitting. If it fits on a single processor, it's a monolithic VC is better.
But this is just by instances solved. And are they the same instances? Is red line strictly more?
Yeah, red line is strictly more.
I see. Because I would imagine that with Hydra 1 core, you would lose some of the simple instances, but you'd gain some of the harder ones.
So, well, I mean, when you take over splitting, you can only do so much, right? Every time you split, you have to kind of backtrack and come back and solve the other branch, whereas it's much more efficient if that is done in the SMT solver itself. Yeah, I mean, so but this doesn't. There will be instances that Hydra solved with one core that Codal didn't solve. There will be instances like that.
And do you apply any simplification afterwards? Like you pick the split point, then perhaps there's certain more aggressive simplification that you can do before going to SMT because you
Not
made
right
some
now.
decisions.
Yeah, it is possible, but not right now. I think what one of the future works that we want to do is to scale to much more than 32. And kind of we're hitting a diminishing returns right now, and so we want to be able to push it to hundreds, of course, and see what happens.
I see. I have many more questions, but I don't want to dominate the questions. All right, one last question then for me. This is all based on functions. And what is your meaning of functions? So for example, in Seahorn, we do all kind of inlining before doing the real inlining. So just kind of what a compiler does. If you have like a get or a set function that's three lines, that's always inlined. What is the notion here? Like, do you mean functions really just functions in the original code?
Yeah.
Like, are they 2-3 lines, or are they 50 lines? Or
you'll have a spread of them. So we don't do any eager inlining. It's all how it was in the source code.
And is there a reason why?
Well, we just let, just for just the engineering of it. So we don't, doing things in the IR is difficult. So we just let the, Codal is meant for inlining anyway. So we just let it take care of it.
I see. And what is your input then?
This is Boogie.
Right, but so who generates Boogie?
So these benchmarks we obtain from the static driver verifier. So it parses C code, C sources of device drivers, does a bunch of processing and spits out Boogie.
So it's not based on some compiler pipeline?
It is based on a compiler pipeline. But it's a little bit different in the sense that the way this architecture is set up is, so Windows device drivers, they compile off Microsoft CL compiler.
Mm-hmm.
And so the way we work with that compiler is that we have it spit out the IR, and that's it. And then we take over, we read in the IR, and we do our processing. And that's how the pipeline works.
I see.
Shall we?
Yeah, I can keep asking questions, but I'm just doing this.
Thank you, Prantik and Akash. Great talk.
Thanks.
Thank you.
Bernhard, do you want to share your screen?
Sure. Oh, I have to wait until Prantik unshares. Okay. Can you see my slides?
Hey, yes, we can see them. Let's welcome Bernhard Codal from IE Austria. Yeah, take it away, Bernhard.
All right, thanks. Yeah, so when I was asked to speak on a workshop on democracy, I was not quite sure what to do since I'm not a social scientist, but then I kind of realized that democracy has something to do with civilization and some of you might know firsthand, verifying concurrent programs can get quite messy and uncivilized. And to address this problem, we are developing a verifier that is called Civil, which is joint work with Shaz Kadir, and kind of builds on previous work that Shaz was doing with other collaborators. So one of the main principles in Civil is to prove concurrent programs across multiple layers of refinement. So the idea is that you can have a low-level implementation, and instead of proving the safety of this low-level implementation directly, you try to construct simpler and simpler programs in a sequence. And then you verify a much simpler high-level program such that there's actually a connection between this hierarchy. So if you prove the safety of, let's say, program PI, it implies the safety of program PI-1. And kind of the reason for doing refinement proofs is to kind of partition the proof into smaller and manageable pieces. And other advantages might be that if you want to replace something in the low-level implementation, you don't have to do the full monolithic proof from scratch, but you just prove kind of the connection of P1 and P2, let's say, and the rest of the proof stays the same. Right. So, and refinement is is not a new idea. However, it's mostly studied in terms of logic and transition systems, in terms of proving simulations between a more concrete and a more abstract transition system. And this is a problem when you want to target programs. And to address this, the idea in Civil is to actually represent each layer in this chain of refinements as a structured program. So on each layer, you have a program that consists of procedures, that has imperative control flow, where you can call procedures synchronously, in parallel, asynchronously, and so on. And each state update is encapsulated in what we call a gated atomic action. And it's kind of a primitive that can model both low-level operations like hardware operations, like compare and swap, but also more high-level operations like releasing a lock. And now the idea is that you kind of keep the connection to a low-level implementation if you do your proof this way. So basically, the philosophy is each layer stays a structure program, but what changes is the level of granularity. So what might be a fine-grained procedure on the lower layer turns into a coarse-grained atomic action on a higher layer. And another distinguishing feature of Civil is that the input is given as what we call a layered concurrent program that kind of gives all these different versions of a program and their connection in a single syntactic piece, which basically avoids the repetition of parts of the code that are shared. And what I'm trying to do in this talk is first give you kind of an idea of what the kinds of program transformations and verification techniques are that are implemented in Civil, and what kind of these layered proofs look like. Then in the second part, I'm going to show you a bit of the interaction of the programmer with the verification system. So this is kind of this, like how do these layered programs look like that the programmer writes. And lastly, Civil is implemented on top of the boogie verifier, and I'm going to give you a hint on how this looks like. And yeah, in this second and third part, I'm actually trying to show you actual code, and I hope this is perceived well in an audience of tool builders and practitioners. Right. So let's start by looking at a simple program where we have an implementation of a lock acquire operation that basically uses a compare and swap operation on a shared variable b. So we have this global Boolean variable b, and to acquire a lock, you call compare and swap to set it from false to true. And in case you fail, you just keep on trying. And on the other hand, if you want to release the lock, you just set the variable b back to false. And we also have a client that now uses this lock to implement an atomic increment. So after acquiring the lock, the client calls a read operation to read a shared variable x. So kind of this procedure sorry, this procedure read here does just an invocation of a primitive atomic operation that reads the shared variable. Then it writes back a value using the write procedure, and finally releases the lock. And what we're going to do now is, in 2 refinement steps, we are proving that this implementation is actually an atomic increment on X. And in the first step, what we're going to do is we transform this lock procedures into atomic operations. So what you see here is that this acquire procedure turned into an atomic action, acquire. And to do this, we actually changed the state representation. So instead of this low-level variable b, we use a more abstract representation on a variable L that is none if no thread holds the lock, or otherwise it is set to the thread ID of the thread that holds the lock. And similarly, to actually do this transformation, we add a parameter. So this is kind of an introduction of local state into these actions, such that the identifier of a thread can be supplied as an input. And so acquiring a lock really just atomically blocks until the lock is available, and then sets the lock to the thread ID of the acquiring lock. And if we want to release, we kind of assert, it's kind of a safety check that the lock is held, and then we reset L back to none. Now, the kind of interesting thing that happens here is how do we establish the connection, right? I mean, we have 2 different state representations. And in Civil, what the programmer does is actually instruments the low-level code with code that establishes this connection. So in case this compare and swap operation succeeds, there's code that atomically, kind of in the same step, using a primitive we call an introduction action, also performs the state update on the introduced state. So we kind of pretend, as in the low-level implementation of acquire, we already have this additional parameter available and use it to update the state representation. And similarly, whenever we set the low-level variable back to false, we also set L to none. And the second thing we actually need to justify this transformation is an invariant that tells us that basically B and L represent kind of the same thing, right? The lock is held or not, but just on 2 different levels of abstraction. And what we do with this read and write procedures is also converting them into atomic actions that do the same. They do reading and writing, but they also make the locking protocol explicit. So we say that whenever we actually want to read or write, we want to do it when we hold the lock. Now, the purpose of doing that is to, before going to that, what we also see is that now when we kind of instruct Civil to convert this lower level procedures to atomic actions, we kind of automatically transfer or rewrite this client into one that now does not invoke the procedures anymore, but it is now one that invokes the corresponding actions. And a neat thing we can do now is attach what is called a mover type to this atomic actions. So a mover type characterizes the commutativity properties of an atomic action. So, for example, acquire and release are so-called right and left movers, and read and writing when a lock is held are both movers. And what this allows us to do is to consider this sequence of operations in this increment procedure to be atomic. So by exploiting a kind of commutativity argument, which is usually called reduction, we can pretend as if there are no yield points where other threads can interfere. So we just consider the code as an atomic block. And by doing that, we can now do a second refinement step that says that the net effect of this acquiring, reading, writing, and releasing actually is just this atomic increment on the X variable. And in the same step, we also hide the lock completely and get rid of the introduced parameter of this procedure, such that we only end up with a single atomic action. And what this means is that a client of this increment procedure can now completely forget that there is a lock implementation on some lower level, and just reason with this atomic increment without writing any invariants about the lock. All right. So to kind of summarize a bit what happens on a transition from layer to layer in Civil is that there is kind of a step from going to preemptive to cooperative semantics, which kind of means that we exploit the commutativity annotations on atomic operations to eliminate yield points, and this is really what we did with this mover annotations on this for actions to show that that ink is atomic. So on the one hand, we have to check that this mover types are actually correct, and then we have to check that the sequences of operations in code follows this sequence, that we have a number of right movers, at most one non-mover, and then a number of left movers. Now the second thing is to instrument a program, a lower layer program with additional state we want to introduce, and we saw that this is done using this introduction actions. And then we kind of going to modularly check that some procedures in the instrumented program are summarized by actions. And by some here, I really mean that the programmer tells us which procedures are going to be converted. And to do this, you can kind of think of what this acquire procedure does, right? It can execute compare and swap a number of times until it finally succeeds. And to kind of avoid reasoning about actual computations, what we do is we use invariants to establish the context for our refinement checking, such that we can do the refinement proofs in some sense procedure modularly. So what we're going to do is we establish an invariant that gives us some contextual information. I like this the connection between B and L. And then what we have to prove is that every execution through a procedure, like say the low-level acquire procedure, is such that it has a number of steps that have no visible side effects. Kind of where I call it executing a skip action that does nothing. Then at some point the atomic specification occurs, and then we again have a bunch of side-free effect operations. And actually, if you want to learn more about a new invariant feature that we introduced called yield invariants, you need to come to my CAF talk tomorrow. Right, and now how this looks like for acquire is that actually all these failed compare and swap operations are corresponding to skip, and the final successful compare and swap corresponds to the atomic acquire. Right, and the final step is now to replace all the rewritten procedures with their corresponding actions and dropping hidden state. And yeah, since I don't have much space on my slide anymore, I'm going to show you the previous one again, where we had that calls to procedures were rewritten to calls to actions. And the nice thing about Civil is that it in one refinement step offers you all of this. These transformations, but the programmer can decide not to use certain things. So for example, if you want to prove a program using just flat invariants and don't do any refinement, you can do it by just inventing complicated invariants. But if you want to exploit mover reasoning and so on, you can, and kind of structure the proof in a very flexible way. Okay, and yeah, now it's time to look at some code examples. Right, so yeah, please let me know if there's any problem with the screen size or the font size, and if you cannot read anything. So
the screen is too cut off on the left. If you can move it a little bit to the right, it would be much easier.
It is cut off. Okay, let me see.
But better, much better.
Okay. So what I have here is a procedure P, and just to say, like, so Civil is implemented on top of Boogie, and this means that we kind of use the annotation feature of Boogie to express concurrent programs. So what I have here is a procedure P that I am declaring as concurrent by saying yields. It's a procedure that has yield points in the middle, and what we have here is just some invocations to increment operations. So we have a low-level increment procedure that is shown without implementation because it's kind of considered as doing the low-level operation, and we're giving it the atomic specification to just increment x atomically given some integer input. And now what this procedure P does is just call increment 3 times in a row. And since this is a concurrent program, we need to somehow capture the interference that other threads might have. So if we say we have a precondition that x is greater or equal to 5, then after the first increment, we need to write an invariant that says that now x is greater or equal to 6. And actually, we cannot avoid writing this because then Civil will complain that there's some yield point missing that we did not specify. But using this invariance to capture interference, we can now prove that when the procedure is done, then x is greater or equal to 8. We cannot say anything more precise because there could be interference of other threads that make x even greater than 8. And yeah, so just to try out, if we would have another procedure Q, and if we would let it decrement x, then actually we will get a number of failures that say that some of our invariants that we wrote are not interference free, because if x was greater or equal to 6, but then we do a decrement, then it might not hold afterwards anymore. Now, to show you a bit of modularity that you can achieve in Civil is I'm showing kind of side by side a different version of the program where this invariants that are kind of not very nice to write explicitly at each line, we kind of encapsulate it in what we call a yield invariant that has a parameter. So here we have yield x that takes a parameter n. And we use this now to capture the interference. So we can write this yield invariant as a precondition and as a postcondition, and now we don't have to write increasing numbers here, but we can capture the interference on x using a single invocation of this yield invariant, right? And what we get out of this is in big examples that are not as contrived as this is kind of some saving on the number of non-interference checks that have to be done, because now we just have one invariant that is checked for non-interference across a number of code fragments, whereas over here we have 1, 2, 3, 4, 5 invariants that need to be checked for non-interference. However, we were not very satisfied yet because writing this invariance is not very nice. And what we can actually do is instead of writing this atomic operation increment, declaring this at atomic, we can declare this both, or let's just write right and say that it's a right mover, because different increment operations actually are commutative. And so what we can do is we can avoid all the yield points between the increment operations and just pretend as if there's no interference from other threads. And just to conclude this small example, one interesting thing to note here is that what actually happens internally is that this procedure P is checked for refinement against the skip action. So if I write this action if I write an atomic action skip that does nothing, what is the problem here? Right, so if I don't annotate the specific operation that a yielding procedure refines, it is automatically the skip action, and this is fine because the variable x that we declared disappears at the same layer as we refine this this procedure. If we would let this variables x survive longer, then actually the refinement check for this procedure fails because now skip does a different update. So this procedure does actually some updates to x which are not captured by skip. And if I instead write this as an increment by 3, then it should actually verify again. So So what we checked is the, so what we checked is that this procedure P actually implements an atomic increment by 3, although on the lower layer it actually is not atomic. Right. And just as a glimpse into the previous example that I was showing you, there is the log example, which starts with a declaration of the type for the log variable L, which can either be none or some thread ID. And here we see that we have to declare the low-level variable B as something that disappears at, in this case, layer 1. And at the same time, at layer 1, we introduce instead this log variable. And after eliminating or after showing that the client performs the atomic increment, we can get rid of the log again, and overall just the variable count on which we perform the increment survives. And yeah, I think I'm going to run out of time if I'm going to show you all the details of this example, but just as a kind of one glimpse here, I'm going to show you the acquire operation, which in this case is annotated with the log invariant that we need for proving refinement, and it also says that it wants to prove that that this implementation that repeatedly calls compare and swap actually refines this atomic action that works on the abstract L variable. And what you can see here is this instrumentation in the case of the success that the programmer writes. So in some sense, this is not part of the real implementation, but here we have this introduction action that captures the connection between a lower layer representation and a higher layer one. Good. Right, and now what I already noted before is that Civil is implemented on top of Boogie, which is a verifier for sequential programs. And kind of to perform this implementation, what happens is that Civil takes as an input this layered concurrent program, which is this kind of concurrent Boogie program with a lot of annotations that tell on which abstraction layers variables exist, on which layers atomic actions exist, and at which point some procedures should be converted into atomic actions and so on. And there's a quite involved layer type checking phase at the beginning of Civil that basically has to make sure that all of these annotations make sense. And what the guarantee of this in the end is that all of these different abstractions of a program, so all of these layers, P1 to Pn, can be automatically extracted from the layered representation. And now after this extraction, we basically end up with a number of still concurrent programs. So what we do next then is to, in some sense, compile away all the concurrency from these programs by basically looking at each procedure of some layer independently. So it's kind of a procedure modular transformation. And the first thing we have to do is that there are sufficient yield points in the implementation. So basically, each procedure consists of a number of invocations of atomic actions and interrupted with procedure invocations or explicitly declared yield points. And the path through a procedure basically has to make sure that if there is no yield point put between atomic actions, then we need to be able to exploit the mover types of the actions to convert something to an atomic block. And then what we're going to do is to make the interference from other threads explicit. So at each yield point in a procedure, we basically have to havoc the complete global state and just assume what a certain invariant at that location gives us about the state updates that other threads might do. And then what we can do is instrument this the code of this procedure to include the checking for both non-interference and refinement. And how this works is that basically at the beginning of every so basically at every yield point, we take a snapshot of the current value of global variables. And then when we reach the subsequent yield point, we have to check if the update that was performed in between is such that it either has no side effect or that it conforms to the specification that some atomic action prescribes. And also what we kind of have to do then on the side is do all of this commutativity checking. And another feature that I won't have time to explain much, but it's called linearity, and basically enables us to get some free invariants on the side that connect variables from different local scopes. Because as you can imagine, if you have to check non-interference, for example, of two different code fragments that appear in different procedures over different local variables, then we sometimes want to have some connection between these local variables without explicitly making the state or kind of exposing these local variables as a ghost global state and writing the invariant explicitly. And kind of overall, what we get out of this is that after all this compilation of, or after compiling away concurrency, we can send a sequential program or a sequential boogie program to C3. So we kind of exploit all the base infrastructure of boogie to do the conversion to logical verification with conditions and parsing back count examples and so on. Right, and so just for a brief demonstration, how this kind of looks like is when we instruct a boogie to also spit out the desugared file of civil, is we get something like that. So let's see. So here we have the procedure acquire that now includes a lot of code that checks for that snapshots global variables and some variables that track the progress on along the implementation of procedures, and at every yield point in this implementation we make calls to parts that do non-interference checking and refinement checking. And yeah, if you're interested in how this works, it's a good way to study this desugared code. Okay, now to kind of conclude, the thing I want to advertise is that all of this tool implementation is publicly available. So Civil is implemented on top of Boogie and actually part of the master branch of Boogie. So if you have a recent version of Boogie installed, you already have Civil, which includes a lot of examples. And here I'm just listing some of the major ones that were done, like a concurrent garbage collector, a race detector, and so on. And what you see here is that a number of researchers, other than the Civil developers, could use the tool to do some interesting verifications of kind of involved concurrent programs. And one thing that I perhaps forgot to advertise at the beginning when I was talking about atomic actions is that that basing the verifier on this notion of an atomic actions allows us to be kind of broad in the number of programs we can handle. So whatever primitive atomic actions we declare in a program, we can also reason about. So, for example, the concurrent garbage collector is a shared memory program that has read and write operations and maybe a compare and swap as a primitive action, whereas some more recent work on distributed systems has primitives like sending a message and receiving a message as a primitive atomic operation. And also what was shown in these papers is that the techniques used in Civil, like mover types, can be extended to have more advanced program transformations to handle things like distributed systems and asynchrony. And just to put Civil kind of in perspective to some other tools, so what we have is that Civil is kind of inspired by the works on TLA Plus and Event B, which were kind of early tools that advocated refinement reasoning. But both of these tools do it on a kind of transition relation representation. So really, there's usually no connection to a low-level implementation, which is one of the things that Civil tries to solve. And a number of more recent projects actually try to do program reasoning on using refinement, but in the background, it's most of these works are still based on a transition relation representation. Then we have a number of verifiers that do concurrency reasoning by kind of focusing more specifically on certain programming languages or programming paradigms, whereas Civil kind of tries to be very flexible in building on top of these atomic actions. But on the other hand, we don't have a compilation to executables, because we're kind of building on top of this intermediate representation, or this intermediate language boogie. And then we also have some tools which are usually called software model checkers, but what I would rather say is that those tools do invariant inference. So they are kind of trying to automatically infer the invariants that are necessary to prove the safety of concurrent programs. And while they are at the moment still limited to rather small examples, we kind of hope that these techniques can be integrated into tools like Civil to help the programmer even further automatize proofs. So Civil kind of offers a lot of structuring mechanisms to partition a proof, but invariants still have to be written manually. And if this can be also automated in the future, it would be a nice thing, and help the adoption of this kind of verification techniques. All right, I think that's all from me. Thanks.
Thank you, Bernard. So I think we're quite a few minutes past schedule right now, but let's at least I see there's at least one question in the chat. If anyone else has a question, please raise your hand and we can ask it directly. So Stephen, do you want to ask your question directly?
Or do I want to answer my question? What did you
No, if you want to ask the question that you typed in the chat.
Oh, okay.
To Bernhard,
So, yeah, so if I understood it correctly, you can correct me. Right mover means that this operation will commute to the right with any other atomic operation from any thread. Is that what that means?
Yes, exactly. So basically what you do is you take the atomic actions that exist on a certain layer. So it also, I mean, I didn't emphasize, but basically what happens is that each layer has a different set of atomic operations. And, you know, for example, to make this read and write that are lock protected movers, we actually have to get rid of the primitive ones that don't lock, right? So really checking these movers is completely, so we take the definitions of the atomic operations without looking at their context in the program.
Okay, so my question was just, you know, what if that condition depends on the state, like the value, the arguments passed in a procedure call? For example, locking on a lock U actually commutes in both directions, left and right, with lock on a different lock V. Mm-hmm. So is there any way to express that? Like, this is a right mover as long as this argument doesn't equal that argument, or something like that?
Yeah. So I guess so in the way I'm specifying locks, the actual lock variable is not passed as a parameter, right? So here this acquire, I'm saying this lock variable L is kind of fixed, and we check commutativity of locking and releasing L with respect to others. And if we would declare a second lock, or let's say L1 and L2, then we would know that they are disjoint. But it is also possible to encode a different representation where we actually pass the lock variable as an argument. And one thing that I didn't have much time to talk about is that actually this commutativity of acquire, release, read and write, and so on depend on the uniqueness of thread IDs, right? So we can only commute an acquire and with respect to another acquire if we know that the two thread IDs are disjoint. And what Sybil does, instead of baking in things like thread identifiers, it has a much more powerful notion of a linear type system that can capture things like unique thread identifiers, but also other things like disjoint memory. So you can pass pointers in that that you know will be disjoint if they are executed by concurrent threads. Yeah.
Thank you.
And maybe one more quick question. So CD, do you want to ask that, or should I summarize?
Hey, nice talk. So like my question is like what can you comment on the differences between like civil and IV? Like, and don't have a lot of information about IV, so just maybe.
Yeah, so I mean, at least the core of Ivy is kind of based on this notion of transition relations, very similar to TL A and event B. So you basically define a number of state variables and actions that act on these variables. And now, for example, if you want to encode an imperative program in this way, you have to make things like the program counter explicit. So you know, some action you have to say, if I am at line 5 in my program, then this action is enabled, and so on. So this is kind of the difference in representation. And the other difference is that what Ivy then tries to do is automatically prove safety by using either supplied or inferred inductive invariance. So I think the main characteristic of Ivy is that it tries to use decidable logic. So it uses a logic that is called EPR, maybe slightly extended EPR, that is known to have a decision procedure, and in this way they try to control the unpredictability of solvers. Although I kind of want to note that still decidability is still not a very good argument, because the complexity of solving EPR is quite high.
Cool. Thank you, Bernard. I think we better get moving. So just for the other 3 speakers that are coming up, just want to note that we're running about 15 minutes late, so we can just imagine the schedule shifted back 15 minutes. Our next speaker, Katerina, could you share your screen?
Yes, I'm trying. Okay, do you see the right thing? I hope you see the right screen.
We see the presenter view right now.
Ah, wait a second. Better?
That's better, yeah.
Okay.
Yes, so good. Katerina is our next speaker. I'll let her introduce herself, and take it away, Katerina.
Okay, thanks. Thanks for the introduction. Also, thank you for the invitation. So I'll just start by saying what I mean by data science software. So this terminology is these days mostly conflated with machine learning software, but I see machine learning more as a subset of data science. So I'll be more precise later, but for now we can just say that data science is any kind of software that takes data as input and then produces outputs that are then used, ultimately used to make or even automate decisions in any sort of field. So this kind of data-driven decision-making software is essentially everywhere now. It's increasingly used we have examples in criminal justice, in banking, in hiring, and even in critical fields like healthcare, and more also in the avionics sector. So at the same time, this causes some trouble. So we had examples in which software used to make decisions turned out to be actually biased. We had cases of critical safety issues, and as well examples of privacy issues and so on. And so where do all these problems come from? So if we go back to the sort of data science representation that I used at the beginning, so this kind of software is is developed in this kind of pipelines that start from the data, then go through pre-processing, some training phase, and then the data analysis, and in the end we get the results out of that. So in this pipeline, what I call machine learning is really what is used for the data analysis. And then data science is actually any kind of software that appears in this pipeline. They take data and then produce something as a result that is then used in the next stages of the pipeline. And so essentially any phase of this pipeline is a source of trouble. So first of all, the data itself is dirty, so it can be inconsistent, can be incorrect, could be, some parts of the data could be missing, so it could be incomplete and it could be inaccurate. So then of course, the first thing that has to be done is to pre-process and prepare this data. And so in fact, this pre-processing phase is where most of the time is actually spent in this data science pipeline. So according to some estimates, up to 80% of the time is spent here. But the problem is that the code, the software is used here is sometimes sort of disregarded as glue code. So it can be written in a rush, and maybe or often poorly tested, and let alone verified or analyzed. And as a result, there could be mistakes in the code that one might not even notice. So the problem is that if the code ultimately gives a result that looks plausible and if the code doesn't crash, we have really no reason to suspect that anything went wrong. And so we'll see some more examples of this later, but this is a problem that comes from this kind of code. Then we have the training phase. So here the idea is to optimize the train system with respect to some metric that should give an estimate on how well the train system will generalize to data that it has previously not seen before. But of course, this estimate is only as good as the data used for the training. So if we don't have enough data, or the data doesn't represent enough data points in some group, maybe group of people or group of data points in general, the train system in the end has fewer constraints on this space, on this input space, and so it's essentially free to do anything it wants. And so that's why, for instance, in this tweet that Geoffrey Hinton put out some time ago, to me, this 90% cure rate didn't mean anything without some idea of what the training and testing set are. And then finally, we have then the train system that we use to make our decisions, or to help us make decisions. And here, in some cases, notably the case of neural networks, the problem is that the systems are generally hard to interpret and often behave in ways that are sort of unpredictable, in which we change just a little tiny bit the input, and this completely changes the output of the system. So essentially, any piece of software in this pipeline is a source of trouble. And that is where our static analyzer comes into play. And so in the rest of the talk, I'll give you a sort of a tour or an overview of the static analyzer. And I'll focus in particular on two things. On the one hand, I'll sort of stop over some of the submodules that are designed to be standalone, so that it can be reused by other tools and for other verification purposes, so not necessarily static analysis. And then the other thing I'll focus on are the domains that we actually design, that we design specifically to solve some problems that come from dealing with data science software. So I won't go into details. Will be sort of a kind of a general overview with some pointers to things where you can get the tools, and to papers where you can read more about the things. So first of all, well, we start from the input, that is the programs. And so Lyra takes as input Python programs, so data science components written in Python. And this is because Python is the most popular programming language used for data science. And this is largely due to the data science libraries like NumPy, Pandas, and so on. But of course, the moment we have Python, well, it's a dynamically typed language. So the very first thing that we have to do is to do some type inference before we can do the static analysis. And so this is done by the first standalone module, part of the static analyzer, which is TPT. So the idea behind TPT is really to turn the type inference problem into an SMT constraint resolution problem. So in that way, any solution to the SMT problem is a valid type assignment for the program. So the TPT takes as input a Python program. It generates some constraints. So some constraints are sort of default, the basic constraints, basic typing constraints, which come directly, they are hard coded and come directly from the Python type system. Plus, there are some other constraints that come from the program, so from the classes declared into the program, so the class hierarchy declared into the program, and the statements that actually appear in the program. All of this is fed to Z3. If Z3 can find a solution, so if Z3 returns Unset, then the model is a valid type assignment for the program, so we can take this and then return a Python program that is annotated with types. And if not, we can actually well construct another SMT problem and give it to Z3 and return essentially a bunch of the minimal set of constraints, type constraints that are conflicting with each other, and this sort of gives an indication of where the type error comes from. So the TPT is on GitHub, and you can so you can find it there. It's a bit outdated with respect to the Z3 version that they built on. As soon as I have a moment, I'll get it up to date. But yeah, it's still fully usable, and you can also read more about it in our CAV paper. Okay, so then after we've done with the type inference, the very next step is to do the generation of the CFG. So this is rather simple. It sort of walks over the AST of the program and generates the CFG from it. And this is then given to the engine of the static analyzer, which will then walk over the CFG and interpret every statement in the CFG into an abstract domain. So the interpreter, of course, then can be configured in various ways. We can then set it to only do a forward analysis, only do a backward analysis, or a combination of the two. We can do the usual inter-procedural analysis and so on. So I won't spend time on this sort of configuration settings. They're rather standard. I think the best resource for this is maybe to look into this is a paper that discussed various trade-offs in static analyzer. This was done for Java, but I think the observations are kind of rather general. So you can take a look at there, what kind of configurations can be done and so on. So we use pretty similar configurations in the static analyzer. So then I'll just move directly to the domains. So these are organized in a sort of hierarchy. So at the very basis, we have the numerical domains. So these are various kinds. So that we have very simple domains that are implemented natively directly into the tool. So these are simple domains like the sign domain and concurrencies and so on. And then we have some other domains that are built instead of the apron numerical also domains library. So these are the intervals, octagons, polyhedra, abstract domains. So for these, so the static analyzer is written in Python. So to interface with the apron library that is written in C, we actually built a little binding module, a little API, a Python API to use the apron library. And this is again some standalone part of the static analyzer that you can also find on GitHub. And it's quite simple and straightforward to use. So we use the C-types Python library for this, which essentially means that the Python interface is quite close to the C interface of the Apron library. So for instance, you have a struct up here in the C code, and this is mirrored in the Python code with another structure that is, again, that comes from the type is defined in the C types library. And then all the functions that are defined in the C API, they are mapped to methods in the Python interface. So really there is sort of almost a one-to-one correspondence between the two interfaces. So if you're familiar with the Apron interface, or even the OCaml and C++ interfaces of Apron, the Python interface is pretty close and ready to be used. Okay, so then the other sort of basis component, basis kind of domains at the bottom layer of this hierarchy of domains are the string domains. And so for this, up to now, we mostly have finite string domains. So we mostly use this paper here from 2013 as a reference. So we have domains like finite string sets, so bounded string sets, in which every variable is assigned to a finite set of strings that or top, which are all represent the possible values that the variable can have. And similarly, we have the character set, so the sets of characters that the strings, the string values of a variable may or must contain. So far this was enough. We are sort of keeping an eye on recent developments on strings. For instance, this kind of work is an abstract domain based on automatas that is more precise for dealing with strings. So far we haven't found the need for it, but we're sort of keeping an eye on it, and we may maybe get into this kind of things up next. Okay, so then these were the sort of two at the very basis of the hierarchy. Then on top of this are the domains that are that we use to abstract containers, so lists and dictionaries and so on. So these are the default abstraction for these are essentially we fully expand the cells of a list or the key value pairs of a dictionary up to a certain bound, and beyond that we summarize everything into a single summary node in which we can only do weak updates. So this is pretty rather standard, and of course we can configure the precision of this abstraction. We can make the bound smaller or larger depending on what we're trying to achieve. Other options that are available that are sort of prototypes, not quite usable yet. There are some implementation made by students of other domains that are more precise for arrays. And this, for instance, this one by Cusoro and Logozzo from Popol 2011. And this one for generic abstraction that works for dictionaries and also arrays, that was in NSAD 2012. So we have sort of prototypes of these two kind of domains into the code base, but they're not yet quite usable when they should be integrated in the main code base at some point. Okay, and then finally, on top of this, we can then have the data science domains. So really the domains that we designed specifically to address issues and challenges that come from dealing with data science software. So the first kind of family of domains is dedicated to performing an analysis related to the usage of data. So in particular, this is something that comes from the, is mostly relevant in the pre-processing kind of phase, the code used in the pre-processing phase of the pipeline, as I showed before. And in particular, the analysis that we sort of developed and targeted is meant to detect whether data remains accidentally unused. So I'll give you an example of this. This happened to these two economists, Reinhard and Rogov. They published this paper here in 2010, in which they did some analysis of the economical status of various countries, and concluded that for countries with a certain level of public debt, the adoption of austerity measures was recommended to recover their economy. So they didn't do the analysis in Python. In their case, they did it in Excel, and they some people later on tried to reproduce the results and couldn't. And then when digging more into what they've done, and they figure out that in this Excel, this analysis that they did in Excel, they made various mistakes. And one of them, in fact, was in computing a formula. They actually only selected a part of the data and missed the rest of that column. And so they accidentally missed some part of the data, and the results, the correct results were actually showing, I think, almost the opposite of their conclusions, or really essentially the opposite of their conclusions. So this was done in Excel, but I mean, similar problems can happen in Python code. And so the problem with this paper was that it was widely cited in political debates. And so some are claiming that it's one of the causes, or it played a part in the economical crisis in Western Europe. Anyway, this is just an example, of course, something that happened in the real world, in a sense. So in Lyra, what we have is then in the study, we have a sort of a general framework to reason about data usage or unused data. And in particular, we have one domain that really builds directly on top of the container domains. So we have this sort of abstraction chunks of a container that are then mapped to a simple domain that really tracks which data is used, not used, or maybe reused, or overridden and so on, overwritten and so on. So it's rather simple, but combined with the other underlying abstraction, it can actually be quite powerful. And then we also showed in our paper that this is actually a more general framework. So other analysis for that sort of reason about dependencies can also be used to, they're less precise, but can still be used to reason about data usage. And so in the static analyzer, we have implemented also domains to perform a strongly live variable analysis, which is less precise than the data usage domain, the default data usage domain, but still a simple analysis that is there. It can also be used for other purposes. And we also showed in the paper that we can then, if we have implementations of domains that are used for secure information flow or program slicing, they can also be cast into the same framework and used inside the static analyzer. So this is not done yet because we haven't found the need for it, but it's still all, it is still possible. Okay, and then a sort of applications, possible applications of this kind of research direction, this reasoning about usage of data. There are various applications that we're looking into. So for instance, one of them is data provenance. So sort of making sure that maybe when merging data, that we preserve the data that is coming from the trustworthy source. So we've been talking with people that work with medical data, and they generally collect data from various sources. And the problem that they have is that when they merge this data, they have some sources that are more trustworthy and some that are less, but maybe have more complete information on this. So when they want to do the merge, they want to keep the information from the trustworthy sources and maybe complement it with the less trustworthy sources, but not override with data coming from less trustworthy sources, for instance. So they're having some ability to say where data comes from is very important. Other applications are in privacy, for instance, and related to that is fairness. So we have some work that is currently under review on certifying fairness for neural networks. And we are now working on fairness for other, in reasoning about fairness for other machine learning systems like random forest and similar things, or support vector machines and so on. So this is sort of on the data usage family of work. And then the other ongoing work that we have is on analysis or domains that can be used to sort of extract the assumptions that are implicitly made by the program on the data that is read by the program. So this is again something that happens very often in the pre-processing phase. So here we have often code that uses magic constants or really is written in such a way that it expects a certain number of data on a line and so on. So I have here a simple example. It's a bit artificial, but it's just to give you an idea. So this is just to compute the GPA of some students, and it's reading some lines from a file. And essentially what this code is expecting is that on the second column of this of each line, the second entry on each line is a number that determines how many grades for the students are available. And then the rest of the code is reading these grades that are in A, B, C, D, F format and converting them into numbers from 4 to 0, and then computing the average. So the problem with this code, of course, well, this code, of course, makes a number of assumptions, and then this can get into trouble when there is a mismatch between the code and the data that is read by the code. So in this case here, for instance, and this is the good case in a sense, here the code will crash because it reads a grade, this B+, that is not expected by the program. The program only expects A, B, C, D, or F. So a B+ is not expected, so the code will crash. What is worse instead is in this case here, where the very first line, it says that there is only one grade for the student DKD. And this first grade that is read is an A. So the average, the GPA as a result for this student will be a 4. But the actual GPA, if you actually read the whole list of grades that are actually present on this line, would be a 3. So the result computed by the program is plausible, but is incorrect. But we don't notice it because the program doesn't crash, and so on. And so this is again another way in which errors can sort of sneak in this phase and not be noticed ever. And so for this, in the static analyzer, we have a domain that again builds on all the other subdomains that that collect constraints on the variables of the program. And then whenever the input is read, these constraints are sort of accumulated into a stack that really mirrors the assumptions made on the input data. So this is ongoing work. I mean, the theory is sort of in place already. The implementation and the experiments are, well, the implementation is essentially also mostly done. We're now working on evaluation experiments and so on. So I'm sort of really all done with the overview. There's the last bit, of course, once the analysis is done, then the analyzer will tell whether the program taken as input is safe, it satisfies the property that we set out to analyze. And if not, it will raise an alarm. And so generally the analysis that we do are over approximations. So then in this case, we might have a false alarm. In some cases, like in this shape, in the input assumptions, in the implicit assumptions of the input data, the analysis is actually sort of under approximating, not quite, but in that case we would get possibly false negatives and so on. But yeah, generally we do an over approximations, and then we might then raise false alarms. So that's sort of the entire overview of the tool. You can find it on GitHub as well. It's actively developed, so it changes pretty from a week to a week. But the other subcomponents that I talked about, the type inference TPT and the Python bindings, are more stable and usable, and they're also again on GitHub. So thanks a lot for your attention, and I'm happy to take any questions you might have.
Thank you, Katerina.
Now, how do I activate my video?
So maybe just a preliminary question before any other questions. Do you have any kind of empirical results or anything to brag about?
Yes and no. So the most of the results are actually on the fairness kind of work. So there we did an extensive experimental evaluation on some neural nets and with real data sets, and there we got pretty nice results. On the other kind of analysis, we have some preliminary things on these assumptions on the input data, but they're I mean, it's preliminary, so I don't know. I wouldn't brag about those for now, but yeah.
Okay. I have a couple of questions, but let's open it up to other questions before those.
I have also a question.
All right, Jorge, go ahead.
Hi, Katerina. So for this shape analysis, is kind of forward or backward analysis to infer the assumption?
Yeah, so yeah, actually both the data usage and the shape analysis are mostly, the main part of the analysis is done backward. There is also a sort of pre-analysis that is done forward to collect some information around it. But the main thing is actually done backward. The main work is done backward. So it's a combination of forward and backward.
I see. And for the, I guess you, by default, you use the inter-procedural analysis, right? Probably, no?
Yeah.
And it's kind of the top-down, starting from main, or
yeah. It's actually rather basic at the moment. So.
And then about the numerical analysis, that there is a, I don't know, which one do you think most of the times is enough for what you need?
It depends. So for the shape, the assumptions on the input data, most of the time, I think intervals are enough. Well, for the fairness work, so, but that's really sort of a deviation as neural nets and so on. There we actually used other domains. There we used intervals as well, but also deep poly, some symbolic constant propagation, and also polyhedra. So it's really a bit of a mess there. But yeah, most of the data usage also we used intervals, but there, I mean, we didn't really do an extensive evaluation yet. So, I mean, it's not a valid data point, I guess.
And just the last question. So for the container domains, you mentioned, I think, that is good enough for you to do like the expansion and then you do a smashing after a while, or or you need to?
I mean, that's the default abstraction that we have, mostly because it was super easy to implement. Of course, for more serious programs, the other more sophisticated abstractions are more useful, but they're actually also harder to get into place and to maintain and so on. So the problem was that the implementations of the other domains were done by students. And so they are in a prototype stage mostly because a lot of the things have changed around them, and so they're not as easily transferable to the new sort of format of the static analyzer, and so they're a bit behind. So they're not as easily, I don't know, made up to date and so on. But yeah, in a practical analysis setting, I guess they would be more useful.
Thank you.
Okay, since there are no other questions, I'll start asking mine. So from the point of view of democratizing software verification, this is a really impressive kind of combination of reuse of existing components and publishing of new components that are reusable and so on. I'm just wondering, in terms of the Python type inference, I'm not super, I'm not an expert on this, but it seems like there are existing tools like MyPy, PyWrite, maybe a few others that can kind of do, they don't have the same kind of SMT based approach, but do you have any thing to comment about why your approach might be more suited to what you're doing in the end? Or could you kind of maybe compare with these other type inference engines?
Yeah, right. So we did at some point compare with them. So in the paper, we actually have a bit more of a discussion on how they compare. So for instance, there is PyType that I remember better. So there, the main problem was that what they do inside is actually a sort of an abstract interpretation based analysis, but the types that they return, so we run some experiments and compared the types that they return and the type that we return. The type that they return were kind of, I would say, less useful. What they're trying to do is to find rather general types, but on a practical point of view, we found that our types were a bit more useful. So what we do is really we take the program as it is. We don't consider the fact that there might be other code that is added later and that uses the code that is there. So it's really a whole program analysis. And so the types that return in the end are really generally the types that are the smallest type, the simplest type that we can find. And this was not always the case for PyType. And the other problem that PyType had back then was that for functions, it really wasn't very good at finding types for functions. So the input and output types. I don't know if they actually updated it in the meanwhile. This I don't know. And instead MyPy, I think they do local type inference, but again, they don't do a whole program type inference. So they don't infer types for functions. And in our case, we actually needed types for functions, and that's why we ended up doing this whole work.
Gotcha, thank you. And in terms of, I mean, if you show your picture again, you had kind of these components of CFG generation and all that. And I'm just wondering, how much of that would be reusable? Say somebody came along and wanted to implement, SMAC or C-horn for Python. Could they start from your IR and translate to bookie or constraint horn clauses in a straightforward way?
I don't know.
Okay, I mean, I guess like what is the representation then of your
so actually
CFG
what we do inside is all so we have a classes for statements, classes for expressions, and all this kind of things. So that part is maybe the least reusable, I'd say. We would have to work more on that. So it was useful because then once you have classes, you can have methods that return things that are useful later on and so on. I don't know. The general design is rather general, but I'm not sure I would, I don't know, I would have to think a bit how one could reuse it more. I think that the two components that I said are really standalone, they're really usable elsewhere. The rest is a bit more too entangled together to sort of be extracted at the moment. It would be nice, I guess, to make it more modular, but yeah.
Fair enough. My other question was for the first class of problems that you talked about in terms of data usage and so on. I'm just curious how kind of a, maybe, I don't know, want to say it more basic or simpler, but you know, IFDS data flow analysis style of approach could compare with yours.
Well, yeah. So, for instance, the simple strongly live variable analysis can also be used in that setting. As I said, it's just less precise. So in our case, we did a lot of work in the domain to determine, for instance, if variables that appear in conditional expressions are have a dependency on the outputs, for instance. So this kind of thing gets a bit lost or is not as precisely captured in this kind of analysis. I think that's the main difference.
I guess the empirical component here that will distinguish them is still being worked on.
I mean, yeah, we don't have an extensive experimental evaluation here. The work there was mostly this theoretical framework, sort of general theoretical framework, and we showed on some instances that, well, we are more precise. And the other advantage is that with this design, we can then combine domains together to perform the analysis. So we can have domains for containers. We can then easily generalize the analysis to lists and dictionaries and so on. Yeah.
Cool. Great. Are there any other questions before we move on to speaker? Well, thank you again, Katerina.
Yeah, thanks.
Our next talk, Jingxuan, go ahead and share your screen. Our next talk, instead of about static analysis or program verification for machine learning, will be listed. So program analysis for using machine learning. Jingxuan is all set up. Take it away, Jingxuan.
Yes, hello everyone. I guess you can see my screen sharing, right?
Yep.
Okay. So I'm Jing Xuan, a PhD student in ETH Zurich at the SII lab. And today I will talk about machine learning based program analysis. So let me first introduce classical program analysis. So given a program, we can run static program analysis. For example, static numerical program analysis, which consists of abstract elements and abstract transformers. After we run the analysis, we can obtain a numerical invariance, which can be used to prove various kinds of safety properties of programs. And we can also run dynamic program analysis or testing. And the most fashionable way now is to fit the program into a fuzzer, and the fuzzer will return a number of test cases. After running the test cases, some bugs can be triggered, or we can measure the coverage of the program with test cases. So designing and implementing such static or dynamic analysis is not easy. So there are usually many different kinds of trade-offs involving in this analysis. For example, for numerical program analysis, there's an inherent trade-off between expressivity and cost. For example, interval domain is the simplest numerical domain, and it's also very fast. And the new polyhedral domain is the most expressive linear relational domain, but it has the worst case exponential time and space complexity. And the octagon domain is in between the two domains. There are a bunch of work that improve the speed of the numerical analysis without in fact the precision of the analysis. Online decomposition is one such example, and it applies to many different relational domains. However, one drawback we found in online decomposition is that it has redundant computation during the inference of invariance. There's another line of work which uses learning-based methods to speed up the numerical analysis, but with the cost of precision loss. The goal is to speed up the analysis as fast as possible and with minimal loss of precision. And the drawback of this work is domain specific. So each of this work focuses only one domain. And it will be very expensive to apply the method to other domains. And also it can incur large precision losses. So for numerical analysis, one generic way to improve the speeds, to speed of the analysis without incurring much precision loss is needed. There's also a trade-off for fuzzing. To test the program, one can run random fuzzing, which is very fast. But since the process of generating test cases is random, so the inputs generated are usually ineffective. As a result, the achieved coverage is low. And one can also run the expensive symbolic execution to generate test cases by symbolically explore the program and solve the constraints. But we all know that symbolic execution can be very slow. So even though the generated inputs are very effective for symbolic execution, but given a specific amount of time, the number of generated inputs are less than random fuzzing. So in the end, the coverage is also low. So to achieve a trade-off between random fuzzing and symbolic execution, parallel work use selective symbolic execution that use heuristics to sometimes run random fuzzing and sometimes run symbolic execution. So in this work, we present two machine learning approaches to address these trade-offs. So we present two works. The first is light, which learns fast and precise numerical program analysis. And this is a joint work with Gaganip, Marcus, and Martin at ETH Zurich. And the second work is ILF, which learns too fast from symbolic execution, and it appears at the CCS, a security conference. And this is a joint work with Mislav, Noda, Pet, and Martin at ETH. So in the next, we begin by presenting light. The key idea of light is that we exploit redundant computation in the analysis. So we just remove the redundant computation from the analysis sequences so that we can speed up the analysis ideally without precision loss. So what is the redundancy in the analysis sequence? We begin by introduce our observation here. So starting from the initial abstract elements, we can run a precise abstract transformer to obtain the next abstract elements. And we can also run a faster but approximate transformer to obtain the next abstract elements. So after running a sequence of abstract transformers, we obtain the numerical invariance in the end. So here we use green to mean that the numerical invariance is precise, and the red color to mean that the numerical invariant is imprecise. So one can obtain the precise invariant by running a sequence of precise transformers, like we highlighted here. However, since the precise transformer is slow, so the analysis is quite slow. We can also sometimes run the approximate transformers to make the analysis faster, but this usually results in imprecise invariance. We observe that we can carefully run the approximate transformers sometimes, and in the end we can still achieve we can still get the precise invariance, like the precise analysis. So here in the two sequences on the right, we run approximate transformers, like the denoted red arrows. So for the two analyses on the right and left hand side, we use less effort, but in the end we achieve the same numerical invariant. This means that the precise analysis in the middle has redundancy. So this redundancy can be really the bottleneck and can be very problematic, as we show. After light removes the redundancy in the analysis, it can actually achieve more than 100x speed up without affecting the precision for some large Linux device driver programs. So after we observe the redundancy analysis, the next challenge is to define and apply the approximate transformers appropriately for redundancy removal without affecting the precision. So here now we introduce light. Light is an approximate join transformer. It learns to drop constraints from the output of join. So here we introduce light by one example. So here we show two abstract elements and a join transformer. The result of the join transformer is an approximation of the union of the two input abstract elements. So after we obtain the join result, we apply light. So first, we represent the join output as a graph. So each node represents a constraint and represent the feature of the constraint. So as we show here, we have four feature vectors. So each feature in the feature vector captures the precision and the shape of the constraints or the abstract elements to measure the complexity. And we also connect the features with the constraint features with edges. And the edges captures the dependency between each constraint. For example, 2 here means that the connected constraints share 2 variables. So the whole graph captures the state, the overall state of the abstract element. After we construct graph, we feed the graph into a graph convolutional network. So the graph convolutional network output a binary decision for each constraint. So if it outputs 1, then we should keep the constraint. If it outputs 0, then we should remove the constraints. Like here, it outputs 0 for the red constraints. Then we remove this red constraint. In the end, light obtains the abstract elements here. So since the output for light has less constraints than the join output, and the time complexity of abstract transformers depends on the number of constraints in the input abstract elements. So the result can actually accelerate the analysis downstream because it has less constraints. So here we introduce how light works in the test time. Now we introduce how to learn light. So to train light, to train light, the core part is to train the graph neural networks, as the features and the graphs are predefined. To train the graph neural networks, we need a supervised data set of graphs where the removed constraints are labeled true or false. True means that removing the constraints does not affect the analysis precision, and false means that removing the constraints loses precision. It means that in the end the numerical invariant is imprecise. So On the right, we show one example graph. The green node means that if we remove this node, in the end, the precision of the numerical invariant is not affected. And for the blue node, we don't label them because we didn't remove them. The first step of the learning algorithm is to run precise analysis on a set of training programs to obtain the ground truth for precision. To obtain the ground truth, that is the precise numerical invariance. So for example, here we have three training programs, and we run the precise analysis to obtain three sequences of transformers, and in the end, we obtain 3 sets of precise numerical invariance. And the step 2 is to run approximate analysis with constraint removal under training programs. So for the 3 training programs, we again run the approximate analysis. Here we approximate twice, denoted by the red arrows. And after we run the approximate analysis, we compare the result numerical invariance with the precise numerical invariance. For example, here, the solid red approximation will result in precise numerical invariance, and the dashed one results in imprecise numerical invariance. So note that, so here our approximation here is Epstein greedy, means that, so in the approximation here, we correlate with 1 minus Epstein probability, or we call a random removal policy with Epstein probability to explore the space of decisions. So after this step, we collected the labeled dataset and trained networks. So for the solid red approximation, we removed one constraint, and the removed constraint does not affect the precision of the result numerical invariant. So we labeled the removed constraints as green. And for the dashed ones, we removed the removed constraints. We label the removed constraints as red. So here we have a supervised data set where we know that the removed constraints are true or false. And then we can use existing optimization techniques to train the networks. And our learning algorithm is iterative, means that step 2 and step 3 can be run for multiple iterations. So step 2 will provide step 3 with more labeled data, and step 3 will provide step 2 with better trained networks. Now we present evaluation of light. So light is instantiated for online decomposed polyhedra and octagon analysis. The implementation is incorporated in the latest version of ININA. The interface is like all other functions in ININA. If you are familiar, it should be fast for you to use it. And we use Codal and LLVM analyzer in the C-home framework to run the analysis, and the analysis is run on SV count benchmarks. So we compare light with a bunch of baselines. First, we compare it with the version of ININA when we wrote the paper. So we use ININA to run the precise analysis. So it generates the precise numerical invariance. So in other words, light tries to remove redundancy from ININA. We also combine light with poly-RL, an approximate analysis with polyhedra analysis with reinforcement learning. And we also compare it with HC, a hand-created heuristics for redundancy removal. So here we measure precision by the number of program points where the generated numerical invariants are the same as ININA. Here we show the results. So for each benchmark, we show the number of program points and the times ININA spent to analyze the program. And for HC, poly-RL, and light, we show the speed up over ININA and the precision of the generated invariance. So for each learning-based approaches, we train the approach on the same set of 30 programs, and we have a time limit and memory limit. So for many time-consuming benchmarks for ININA, poly-RL can achieve a huge speed up with It's usually perfect precision. On the contrary, HC can be imprecise, even though it can be faster. And poly-RL, the speed up of poly-RL is very modest compared to ININA, even though it can keep the precision. And for benchmarks that ININA, where ININA are very fast, which usually means that there's not much redundancy. Light can also keep the precision to almost the same level as ININA. We'll also run the analysis on around 200 programs where ININA does not finish within 2 hours. So HC can finish around 100 programs, and poly-RL can finish 50, and Light can finish the most on 125 programs, and it's also faster than HC and poly-RL. So Light actually pushed the limit of polyhedral analysis. We also run Light and HC on octagon domains. So here, even though ININA is quite fast on octagon analysis, Light can still achieve some speed up, on average 1.3x, with close to original precision. Here, for the MD mode benchmarks, ININA is very slow because it does not converge for like hundreds of iterations, and Light actually speed up the convergence with the approximation. Okay, so that's the result for the Light. So in the second part of this talk, I would like to talk about ILF, which learns too fast from symbolic execution. The key idea is to apply a specific kind of learning, which is called imitation learning for fuzzing, and it's instantiated on smart contract testing. So we first introduce smart contract. So in the left-hand side, we have an example smart contract, which has a field owner and has a bunch of functions. Smart contract on the high level is a state-based program. So the owner here has different values, and it represents different states of the wallet contract, and it has different functions. The constructor is used to construct the smart contract, and the owner will be set to the sender, to the constructor, to the person who construct the contract initially. And we can use the set owner function to change the owner. And we can use the deposit function, which is payable, means that you can pay money or ether to the contract. And one can also withdraw the amount of ether that is deposited in the contract. But the withdrawal requires that the person who calls the withdraw function should be the owner of the contract. And since smart contract is a state-based program, from the initial states, which is after the construction of the contract, we can call a number of functions to change the state of the contract. So we can have plenty of choices. And next, we can also call more functions to change the state. So the state space of the smart contract is really exponential in terms of the depth, like the number of calls, the number of transactions from the initial state. So here, actually, the smart contract has a bug, has a vulnerability, so that one attacker can steal ether from an innocent person. So to trigger the vulnerability, so an innocent person first deposits P ether into the contract. Then an attacker set herself as the owner of the contract, and then the attacker can withdraw the P ether from the innocent person. So for smart contract testing, what we want is that we want a sequence of transactions or function calls that explore the state space of the smart contract very deeply and thoroughly. Because of the because of the trade-off for fuzzing, as we showed before, random testing can usually be ineffective, as well as symbolic execution. So in this talk, our idea is to in this work, our idea is to use imitation learning. So I will introduce on the high level what is imitation learning. Suppose you have a very label-intensive task that you want to finish. What you can do is hire a human expert, right? But a human expert can be very expensive. So ideally, what you want is you want a robot to perform the task for you. And then how do we obtain such robots? A human expert is to demonstrate to the robot how to perform the task. So in a machine learning perspective, the expert should perform the task him or herself and generate a training data set for the robot. And the robot can learn machine learning models from the data set, and then it can learn to perform the task you want. So here in our setting, we use symbolic execution to demonstrate for fuzzer. So in more detail, we now present the general framework of learning to fuzz from symbolic execution. So it consists of two phases. In the training phase, we have a large number of programs or smart contracts. Here we have like 15K contracts. So on these contracts, we run a symbolic execution expert. So because the symbolic execution expert can solve the path constraints to generate test cases. We have the transaction sequences generated by the symbolic experts are actually very effective. Then we use the transaction sequences as a data set to train a fuzzing policy, which we use neural networks here. The fuzzing policy tries to imitate the symbolic execution expert, but it can be much faster than the symbolic execution expert. So in the fuzzing phase, we have a new contract, and we input the new contract to the neural network-based fuzzing policy. And the policy will generate a number of test cases. The test cases will report coverage for the contract and maybe uncover a set of vulnerabilities. So next, we will introduce these components one by one. First, we will introduce for the fuzzing policy. So the general framework of smart contract fuzzing is that we have a fuzzing policy and a tested contract. So the fuzzing policy keeps sending transactions or function calls or inputs to the tested contract. And the tested contract sends feedback to the fuzzing policy to improve for the generation of the test cases. So the transaction will modify blockchain state as we showed before in the example contract. And the transaction consists of a function call and the sender of the contract and the amount of ether to pay. So we can decompose the fuzzing policy into four components: the function, the arguments, the function arguments, and the sender and the amount of ether to pay. We can actually view the fuzzing policy as a probabilistic distribution over all the possible transactions. So the fuzzing policy consists of four different probabilistic distributions. So here we have an example, which is a uniformly random policy. So the distribution for function is a uniform distribution on the set of possible functions to call. And after we select the function to call, then the distribution for arguments is a uniform distribution over all the arguments that complies with the selected function. And the distribution for sender is a uniform distribution over possible senders, a predefined set of possible senders. And the amount of ether to pay or money to pay is a uniform distribution between 0 and a maximum amount when the function is payable. And the distribution is always 0 if the function is not payable. So here we have an example of uniformly random policy. So actually we can use a neural network to represent the fuzzing policy. The inputs so the neural network fuzzing policy each time generates a transaction, and the input to the network is features of functions that can change dynamically after each step. And the output of the neural network fuzzing policy is 4 distributions. And from the distributions, we can sample the components of the transactions, and we send the sampled transaction to the smart contract, and we obtain feedback, and we keep doing this in the next step. So now here I will not show the details of the neural networks, and the details can be found in the paper. So here we have the fuzzing policy. Now we need to define the symbolic execution expert. So as we told before, the number of states is exponential in terms of the number of transactions. So the symbolic execution expert works like follows. It's actually greedy in terms of achieved coverage. So from the initial block, the symbolic symbolically execute the program and find the test cases that can achieve the most coverage in the current state, which is T1. And it generates a transaction, a concrete transaction, and then it concretely executes the transaction, and we will move to the next block state. And from this state, we again select the branch that can improve the coverage the most and generates T2. And then we keep doing this. After that, we can revisit the previous block state to seek opportunities to improve the coverage more. And the symbolic execution engine is the VerX framework, which appears in SMP. And now we introduce how to learn fuzzing policy from the generative sequences. So for each step, we run the transactions generated by the symbolic execution expert. And we also run the inference of the neural network policy. And the inference will generate 4 probabilistic distributions. And we compare the distribution with the transaction generated by the expert. And we can compute some loss, and we can backpropagate the loss to the neural network policy. So this will make the policy tries to perform like the expert, tries to force it to perform like the expert, so that the distribution generated will assign the highest probability to the parameters selected by the expert. And then we run the transaction generated by the expert and go to the next step, which is the same as we showed here. So now we have an evaluation of the system. The system is available at this link in the bottom, and we evaluate on around 20K contract and compared with a bunch of baselines. And we have different experiments to show the effectiveness of this approach. And we compare the IIF with a bunch of fuzzers. We show that IIF can achieve higher coverage than the fuzzers. And we also compare it with the symbolic expert. So here in the green bar shows the coverage of the symbolic expert, and the yellow bar shows the result of IIF, the coverage of IIF when we run the same transaction as the expert. So when we run the same transaction as the expert, actually IIF can achieve lower coverage than the expert. This is because IIF learns from the expert. But however, since IIF is much faster than the expert, if we run 200 transactions, which usually takes like 10 seconds, IIF can achieve much higher coverage than the expert. And the expert use like meanings to achieve this lower coverage than IIF. And we also show that IIF can find more vulnerabilities than existing systems. Here here comes the summary of this talk. So we introduced two parts in this work. The first is about learning to speed up numerical analysis, and the second part is about learning too fast from symbolic execution. Thanks, everybody. That's the end of the talk.
Thank you, James Ron. So, questions from the audience? Yes, Katerina? Oh, that's a clap. Questions from the audience?
I also have a question.
Yes.
But can you go back to the experimental results with the first part?
Yes, one second.
Sorry. Oh, yeah.
So for which one? For Hydra?
That Hydra is fine, yeah. Okay, so the first question would be, I mean, here you're just removing constraints, so the analysis is in any case is always sound, right?
Yes.
Okay, so and the other question was, like, in the cases in which the precision goes quite a bit down, like 80, 83, and so on, do you have any indication of why that happens? Like, what happens in this kind of, I mean, is it something in the programs, or is it, yeah.
So here sometimes for this CX25840 benchmark, the precision of light drops to like 83.
Yeah.
It's usually like so the precision is quite vulnerable to decisions made by this kind of approaches, right? So if you make a wrong decision in the middle of the program, and then the precision will carry down towards the end of the program. So all the points between the middle and the end will be affected by the wrong decision, right? So
right.
If it's usually like this, we made a wrong decision in the middle of the program, then the imprecision carries down to all the programs along the path.
Okay, but then do you have a way of sort of figuring out where you made the wrong decision and sort of maybe use this information to I don't know, improve the training of the system or something?
I mean, yes. I mean, in the training algorithm, right? So the training algorithm is iterative, which means that in step 2, sometimes we made the wrong decision, right?
Okay.
And then we go back to this again, like in multiple iterations. So it will try to correct the mistakes, but in the end, it still has some mistakes.
Yeah. Okay, thanks.
Next question for Scott.
I had a question about the second half of the talk.
Yeah.
So I guess my first question is to clarify is, you're learning the policies from like one set, and then you're applying it to a contract. Oh, contracts or other stuff, like the policies learned and then it's fixed, right?
Yes.
Okay, so you mentioned one of the models you learn is for the names, right? The names of the methods?
Yes, yes.
Do you have any thought on why that might generalize? Do you think that might be because so many contracts fall into specific, like following specific patterns, that the names get used over and over again? And that is like, because I imagine in general, if you're just looking at random programs, the name of the method probably wouldn't predict what method to call very well. So do you have any idea why that's effective here?
So first, smart contracts are similar, right? Like
yes.
We have like quite some standards, and also the behavior of smart contract can be simulated as shown in Michael's PRDI 20 paper. So that's the main observation we use, so that we can like train on a set of contracts and test it on new contract. And so for the function names, so since there are quite some standards, the function names can be similar. And another thing is that for function names, we actually, to represent the function names, we actually use the embedding, right? The embedding, so because function names are natural language, we use the natural language embedding, which is a vector. So we represent each function with a vector, a numerical vector, and then the embedding vector will capture semantically like what the natural language means. So this is another explanation for the generalization.
Do you think it'd be even more effective if you took all the names of the methods? Because like you said, there's like certain standards like ERC training, and there might be like codes where those look familiar. So if you looked at the embedding of all the methods, it might be able to hone in on what kind of protocol it's following and then make even better selections? Or do you think that would take away from, like, do you think that, my background isn't really in machine learning, so that's why I'm not. If that seems like
yes.
Okay.
So for, let's say for certain standard, for one standard, it maybe is very, it will maybe effective to just collect all kinds of method names and represent them somehow, like use some embeddings or whatever, or use some abstractions, but it will not generalize to new standards, right? New kinds of contracts.
But is there a reason why two separate standards should generalize if they're not the same standard anyway? Just based on the name of the methods?
I mean, so for example, one example is that usually contracts has setters and getters, right?
Yes.
If there's a setter, it has some, it usually means that it sets something. And this kind of things is general in like across different standards or different sets of contracts. But if you model the full name of the setter or getter, then you will not get it will not be generalized. It will not generalize to different standards. Right?
Wait, so then how do you generalize that? I think I'm misunderstood. So the way we model the function name is that we split the function name into subtokens. Okay.
For example, setters will have a subtoken set, and getters will have a subtoken get. And this for this we will know that this function is a setter or getter.
Okay, that makes sense.
And yeah, this we will
Could you also take advantage of other pieces of the function signature, like, you know, that this is a, I forget the terminology, but like a read-only operation versus a mutator versus this kind of thing?
Yes, this is quite possible. Yeah, it's a like the mutatability of the function, for example, or name of the arguments or type of the arguments. But in this work, we only use function names. Yeah.
Okay, next question from CD.
Yes, can you hear me?
Yes.
So,
yes.
So like my question is about like the tests that you generate that the network learn. Like, do you learn this test like from specification? Because like from the example you gave, like it's hard like to see whether the vulnerability is corresponding to a violation of the specification of that contract. Like because
yes.
there is no failure of the test. Like there is no assertion that failed. It's just like
yes. Yes. So for the vulnerability, we have different kinds of vulnerability, right? So each vulnerability consists of a specification to check. Yes. So so on the high level, the specification of the vulnerabilities. So given a set of a sequence of transactions to check, and the output of a specification will be like violated or not.
Okay, if I understand, that means that you have some prefixed specification.
Yes, yes.
Testing.
Yes.
Okay.
So yes, in smart contracts, there are different types of vulnerabilities, right? So the specification are already predefined. Yeah.
Yeah, because like yeah, you will not do testing on any arbitrary contract for like for its high-level functionalities to test whether this contract like violates some high-level functionality, because like the specification are already predefined.
Yeah, here we only do like generic vulnerabilities, generic specifications. It's not for specific contract. Like it's not a, so the vulnerability here is like a general across all contracts. It's not like per contract.
Would this be like overflows and things like that?
Yeah, something like for example, as we showed an example, like attacker cannot steal money from other people, something like that.
Okay, nice. Thank you.
Okay, and another question from Shuje.
Okay. Thanks. Yeah. Thanks for the interesting talk. I'm curious about the features you mentioned in either analysis or fuzzing. You have certain kind of features. So I wonder how they are designed and how significant they are in terms either training or in terms of accuracy. Because the key advantage of this deep neural nets is to avoid this kind of feature engineering. But it seems like here features actually matters a lot. So can you comment a bit on in terms of that?
I mean, so yes, for this system, features are very important because, so for example, for the analysis, the features captures the complexity of the abstract elements or the precision of the abstract elements, and the features for fuzzing capture the state of the fuzzing, like how many times a function get called, something like this. So for, I think defining the features are necessary for our works, because otherwise you need to obtain some, you would use the network to extract some features from the low-level representation or something. But that will be, in terms of programs, like for example, here we do program analysis. We would like to extract from like low-level representation, like polyhedra constraints, or for fuzzing, we would like to extract from execution traces too. And this would be, I think this would be very computation expensive, or I don't know how to, I don't have a direct thinking how to like extract from very low level representation, extract features from low level representation to make it useful on like very complicated analysis or testing. So there are also actually some works on neural network verification where they also extract the features from the neural network. I think the feature extraction step are necessary.
Another thing I'm curious is the feature development process. Do you guys first come a whole bunch of features, then you end up say, okay, this subset is useful, or maybe you actually add new features by need based on whether you have better accuracy? So yeah, can you comment a little bit?
Yes, the process is like, so first we have ideas on the initial set of features based on our experience and the intuition, and then we keep adding features to keep adding features and then see whether the accuracy improves. And so for the first part, there are actually some analysis of the features, like the importance of the features in the paper.
Okay, great. Yeah, thanks.
Okay, before we go to the next talk, I just have one more softball question that I feel compelled to ask. So in late, I mean, you described, the machine learning to drop basically conjuncts of the constraints that you're using in your abstract domain. What I'm wondering is how specific that is to numerical analysis. For instance, could I think of applying the exact same technology to something like predicate abstraction based analysis, where I would like drop different, predicates in the cubes that I'm propagating around?
Yes, that's yeah, I think it's possible. And if you want learn to do this, you need a way to generate like to decide dropping which constraints is good or not. Right? You need a data generation process where you use your domain specific knowledge to determine the labels of the dropped constraints.
I guess then maybe a natural question is why you chose to go to target numerical program or numerical domains rather than other kind of conjunction based domains.
This is because we have our lab has been developing the inlining numerical domains, right? And we have experience and
Gotcha.
the framework on this. And we also think that the constraints, like numerical constraint-based representation for numerical domains, is quite suited for these kind of approaches, because in the conjunction-based, like for example, for point analysis, the representation is kind of more discrete and would be harder to extract features, etc.
Yeah. Okay, looks like there are no more hands raised. Great, thank you, Jingxuan.
Thank you.
Our final talk, Alex, if you could share your screen, will be by Alex Summers, also of ETH. Well, formerly of ETH. I let him introduce his newer affiliation. Alex, are you around?
Hi, yeah. Can you hear me?
Yes, yes.
Great.
Take it away, Alex.
Thanks. So indeed, I'm not actually at ETH anymore. I moved to the University of British Columbia this year. So thanks very much for the invitation and the chance to talk about Proceedings, which is a project that I'm running, have been for a little while, but it's indeed in collaboration with a whole bunch of people at ETH. So this is joint work with Vytautas and Christoph and Federico and Peter. And in particular, Vytautas and Federico built the first version of the tool that I'll be demonstrating a bit later. So the talk is about how we're building verification tooling for Rust. But I thought I'd start off by talking instead about a different language. So here's a little toy program written in C or some C-like dialect. And what the idea is I've got a couple of pointers to what are supposedly lists, and my little toy sequence of code just takes the length of one list in some way and then appends an element to the other list and then tries to assert that the length of the first list has not changed. And now, since I'm speaking to a verification audience, I guess people might see a number of ways in which this assertion may or may not hold. So I'd like to prove this dysfunctional property, and the way I'd like to prove it, incidentally, is also with a modular technique that doesn't necessarily require me to know the implementation of append, but I think the initial problems arise whatever technique you apply. So one is we might not even get to this line, right? So the program could already crash, for example, because B turns out to be null and I dereference it in the first line. Of course, another possibility that probably jumps out when you stare at the example a little is These two lists could be aliases of each other, and that could be simple aliases in that the pointers are the same, but it could also be something more complex in memory. For example, they kind of join at some point in the middle of the lists. And so then this property may or may not be true. And then, I mean, thirdly, there could be concurrency, right? These days, more and more program is concurrent in one way or another. If there are threads that are interleaving, threads that are concurrently running with this code, in a sense, all bets are off for this kind of local reasoning about what the code is doing. All of these data structures in memory could have been arbitrarily changed at every point in the program. And you kind of need to worry about these three issues as a programmer in these kinds of languages. And if you want to verify something about these kinds of languages, you also need to worry about these kinds of issues, essentially regardless of what you're interested in proving about the program. So, of course, this is not a new problem, and there have been many, many attempts in the verification community at formal techniques for attacking verification for these kinds of languages. And for those techniques which are trying to develop kind of modular proofs for these kinds of programs, then typically you see the following kinds of ingredients show up. So one is you end up with some kind of additional ghost state or assertion language that lets you describe some notion of ownership or permission to access some parts of the memory. This could be like the linear types that were mentioned in the civil talk earlier. There's a whole different range of flavors of these kinds of assertions, but something which prescribes which parts of the memory are going to be accessed and in which ways. And then typically you need to lift these kinds of assertions to some kind of unbounded data structures in the heap. So you might have something like predicates that describe entire linked lists, for example. And then many of these techniques involve some kind of way of talking about disjointnesses. So you want some way of saying there's disjointness in memory. And so this star comes from separation logic, which is probably one of the more famous families of formal technique in this area. You want some kind of way of saying that I know about two parts of the memory and they don't overlap in any way. And then you can take these kind of formal reasoning techniques and you can build tools for them. And typically, if you want to automate the proofs for these kinds of techniques, you need some kind of auxiliary annotation as well. You need to do some of the work yourself as a verification engineer. So I thought I would start off by just giving you a flavor of what this is typically like to use. And since I have tools kicking around, can you see the code now? And would anyone like it larger?
Looks good to me.
Okay, great. Thank you. So this is a little example in the Viper intermediate verification language. So Viper is a project which is also close to my heart, but this is not going to be a talk primarily about Viper, but it's designed for enabling people to build tools for these kinds of formal techniques for heap manipulating concurrent programs. And so here is a little coded up version of an append. And in Viper, everything on the heap is just called ref. So the type system is very simple. And so the idea is I'm taking a reference to what is probably a linked list, and I'm going to try and stick an extra element on the end. And then this is implemented in pretty much the obvious way. Of course, the syntax might not look completely familiar to you, but I think it's reasonably readable. On this line, I use the macro for allocating a new node. I can show you the definitions if anyone's particularly interested. But allocation is not built in as such in Viper. But essentially, we walk through the list until we find the end, and then we stick an extra node at the end. So now Viper is unhappy with me, which is not a particularly uncommon occurrence. And in this particular case, it's complaining that I'm accessing the heap, and I've not explained to it why I have permission to do so. So in Viper, we have these specifications for talking about which parts of the heap I have access to. So a kind of trivial way of making that problem go away is to add a precondition where I say, I have these are called accessibility predicates, but I have the ownership or the access right to the heap location a.next. And now my problem has gone away, but of course it didn't really fix the problem. So now I've pushed the problem somewhere else. And it turns out that the problem is now on the recursive call. If I want to recursively call append on a.next, I now need the permission to a.next.next. And of course I could add that here, but that's going to push the problem one level deeper still. So one way to fix this problem is that I define one of these predicates. So I say I would like to be able to describe linked lists in the following way. So a list at X means that I have the access to both the value stored at X and the next field stored at X. And then if if the next field is not null, then there's also a recursive instance of the same predicate at this location. And so now what I'd like to write, instead of just enumerating each individual field in the heap, I'd like to say, well, I have access to the entire list starting at A. Okay, now Viper is unhappy with me again. And it turns out that Viper doesn't peek inside predicates for free, in a sense. So if I want to reason about these predicate definitions, I need to tell Viper when to look inside the body. So when to exchange a predicate instance for its body. And now this verifies, but is maybe not super useful because I don't give any of these access rights back to the caller. And if I want to have a post condition, which also says I end up at least with the list at A, then I need to do a little bit more work. So I need to do the analogous. Let's see, I probably need to fold again to assemble the list. And I also need to fold at the point where I've assembled my new node. Something like this. Okay, and now Viper is happy, and I've done this work just to persuade Viper that the way I'm accessing the memory kind of follows the rules. So you'll note I did a moderate amount of work here, and I haven't actually proved anything about what the program does yet. So all I've basically written now is a specification which says, well, you start with a list and you end up with a list. I mean, that specification would also be true, of course, if I just deleted the entire method body. So somehow this is not super useful yet. So Viper can be used to verify much more complex functional properties of code. I won't go into that too much here, just to give you a slight flavor of the kinds of things we might like to do. So here is, for example, an extra function that I've written which computes from the heap the length of a list. So you can write functions that can then be used in specifications. So these are mathematical functions of some part of the heap. And now I can verify, in addition, the kind of toy example from my first slide. So we can do a lot more in Viper. And if you're interested in sort of arbitrary new formal techniques for these kinds of programs, particularly if they have some kind of modular flavor, then the idea is Viper is supposed to be usable as an intermediate language for compiling those proof techniques down. But let's sort of zoom out again and think a little bit about what we've seen. So I wanted to show you what this is like to use. Well, essentially imagine now that you scale up to a reasonably sized code base. This is still not that many lines of code. Of course, you're not meant to read these lines of code on the slide. What tends to happen now is there's just an awful lot of this work over and over again. So you have to write a lot of annotations, you have to introduce appropriate predicates, you have to write a lot of specifications. This ultimately requires someone who is highly trained in verification. You need to understand how to introduce, say, recursively defined, these are basically fixed point definitions of predicates, and how to annotate the program in the right way and understand the intermediate verification states, etc. And all of these steps are kind of necessary just to get started in one of these methodologies. So like I say, even if I don't prove anything yet about what the program really does, I still have to do essentially all of this work. And in the rest of my talk, I'd like to describe this kind of mandatory initial effort as what I'll call the core proof. So what the kind of minimal effort you have to put in just to get this program accepted by one of these proof techniques. So then we got interested in Rust. So this is the same kind of toy program written in Rust, and it looks superficially pretty similar, except now you'll see that instead of the star for pointers, I've got this interesting and mute notation for some kind of reference. But this is basically the analogous program in Rust. And remember the problems that we discussed. So I'd like to prove this rather simple functional property about the program, but before we had to worry in addition about memory errors and aliasing and data races. But it turns out Rust's type system has this ownership kind of flavor built in. So in particular, the meaning of this function signature is not just that A and B are references, they're references which give me exclusive mutable access to the list and everything reachable from the list. And this exclusive access implicitly tells me, in fact, that the two lists can't alias each other anywhere all the way down. It also tells me, incidentally, that A and B can't be null. So there's no null as such in this type. If you want something like null, you have to use option types, as you see in various other languages. So now it turns out the problem of memory errors goes away essentially by construction. The type system has already ruled out the possibility, for example, that the first line would crash. And similarly, aliasing has been very tightly controlled compared with the analogous program in something like C or C++. So a lot of the information that I need for verification now comes from the type system itself. And it turns out the analogous story works for concurrency. So the way Rust handles concurrency, at least by default, is that the type system will again be used to keep track of which threads have which access to which parts of the heap and to rule out data races. So now a lot of these basic issues that have to be kind of in the back of your mind all the time as a C or C++ programmer have been taken care of at the language level. The question we asked is, can we indeed exploit this type system also for verification and somehow make this baseline effort somewhat easier? So, oh, that seems to be a duplicate slide, sorry about that. So I'd like to show you a little bit how this could possibly look. To do this, I'll switch to a different tool. So this is actual Rust code. I don't know how many people have seen Rust before. It's been around for a few years now and seems to be getting more popular as time goes on. And this is indeed the same little example with a bit more colorful syntax highlighting written in Rust. And so what happens here is I have, oh, let me get rid of my Viper information. I hope you can see the display at the bottom as well with the error message and the output that says verification failed. So, okay, firstly, this little snippet of code fails. Can anybody see why? There's a good reason, not a, not an annoying tools reason why this fails.
You're appending to B?
Yes, exactly. So there's a copy paste error in my code, and it's not actually the code that I wrote on the slide. Indeed, thanks. So now if I fix the code and append to A, and then run the thing again, so now this program verifies. And I mean, this program verifies with little effort on my part. So let's take a look through the file and see what I've actually done. So firstly, this is the analogous struct definition written in Rust. So structs are similar to structs in C and C++. Some of the types look a bit different. Here we have the option type so that we can effectively make next null when we need to hit the end of the list. Boxes are owning pointers in Rust, so it's just one more level of indirection in the type. This is the type signature, as I explained before, and in particular that gives this unique ownership to the list all the way down property. So let's scroll down a bit. This is the implementation of append. And again, a lot of the syntax might be unfamiliar if you haven't seen Rust before. In particular, what I do here is just a fancy kind of stylized pattern matching. Essentially, it's just a way of saying if a.next looks like a sum from the option type with a box inside it, and I can then take a mutable reference to the tail basically as part of the pattern match. And then, so it's essentially just one case of a pattern match. I could have written this differently with an explicit match statement. Then we recursively call append. And otherwise, this is how we build a new instance of the struct. So this is really doing the analogous thing to what you would do in other languages. And then let's look what else. So I've defined this len function. This is again all Rust code. The only annotation I've added is this pure one, and this will be useful later. So this will allow me to write len in specifications. It also means that our verifier treats len slightly differently when verifying this client code. In particular, pure says not only are we going to use this in specifications, it essentially declares this as a mathematical function of the part of the heap that is accessible according to the Rust type system. And that enables this kind of framing story where we know that this call and this call must return the same value because they talk about a disjoint part of the heap from what append could access. Does anyone have any questions at this stage? I'm also happy to answer questions about Rust insofar as I can. If not, then I'll move on to something a little bit fancier. Okay, I'm assuming there are no questions. I don't think I can see the chat, so if there's something in the chat, then please somebody shout and let me know.
Nope, there's nothing in the chat.
Okay, great, thank you. So now this is just a slight variant of the same file, but I thought I would add a bit more to it just to show you how things start to go if you want to say something a little bit more interesting about the program. So what have I done here? Well, oh, I've skipped ahead slightly. I didn't mean to put that in yet. So this is my length function as written before. So one thing we can start adding as annotations are specifications. We can add things like pre and post conditions to functions. And now these are picked up by the verification tool and indeed proved. In this case, we prove in the kind of typical inductive fashion that len satisfies this post condition to show you that it's not cheating in some way. If I try to prove instead that the length is always greater than 1, then indeed this verification will fail. Okay. So all of this is Rust code, incidentally, and you might wonder why it takes a little bit of time even to verify very simple programs. Well, one reason is we're running the Rust compiler every time. So this tool is a plugin for the compiler itself. And so parsing and type checking and building a representation of the Rust program is not really done by us. We plug in instead to all of the representations that the compiler uses. But everything you see with a hash in front of it like this, these are annotations that you can add to Rust, and these particular annotations are picked up by our tool. So now, to give you a little more experience of Rust, and also because I can then write something slightly more interesting in this example, I thought I would show you what happens if I add, say, a simple getter function to my list type. So here I'm taking a reference to the list. This self means it's like this in Java and other languages. So I'd like to fetch the index, I can't quite say that, element of the list. And so how do we do that? Well, the code is not super difficult. So one thing is if we're at the right position already, so if index is 0, then I'd just like to return the value that we have here. And then what do I want to do otherwise? Well, I guess the simple idea would be I'd like to essentially recursively call get on self.next. So one way to get hold of self.next, and this time I'll write an explicit pattern match, is I pattern match it, and it should be a sum of a box, and I want a reference to the tail. And then I'd like to recursively call get on the tail and index -1. So now, and I've got the syntax wrong, sorry. So indeed, since this is a function of self, the way I've written it, then you have to write the call like this. So now I get an error from the Rust compiler, and it says, well, this is non-exhaustive. I've written a match over an option type, and I've only written the sum case. So that's kind of fair enough. But what do I want to write in the none case? This is sort of awkward. I mean, the idea is I'm going to find the element eventually if I keep on walking down the list. So one way I can persuade the Rust compiler everything is fine is I can use this unreachable in Rust to say, well, essentially this code is never hit. So that solves the compiler error, but now our tool jumps in and complains. And instead, Proceedings complains now that it can't prove that this unreachable statement is indeed unreachable. And if I step back a minute and think about it a bit, it's not actually true. So I haven't said anything about indexes being in bounds here. And so you could, of course, call my function in a way that would make it crash now at this unreachable line. And in order to rule out that possibility, then I should add a precondition, and the precondition should indeed say that index is in the range. And in the precondition in particular, I can use the function that I've defined before. So I'll use len to bound index. Okay, and now I sit and let it run, and now verification succeeds. Again, if there are any questions, I'm happy to be interrupted. Otherwise, I'll just write one more function. So now I'll write something like a sorted function on lists. And this is going to have a similar pattern matching structure, but it's slightly simpler, in fact. And sorted needs to say, well, if there's a next, so I'll use the same sum box ref tail. If there's a next, then let's make it sorted in ascending order, I think is what I did before at least. Although I guess it should work either way around. Then self.val should be less than tail.val, and tail should also be sorted. And of course, if we're at none, so if there's only one element in the list, then it's sorted trivially. Okay, so I mean, this can't fail to verify because I didn't write any specification about it. But in particular, I can now go back to the client and I can play with the specification here. So one thing I could say is actually, I only want the client to be called, oops, sorry, my syntax is wrong. I only want the client to be called in situations where, let's say, which one, A is sorted. And then I'd like to guarantee that A is sorted afterwards. And probably, if you stare at that for more than a moment, you might think, well, actually, that sounds a bit fishy. It probably shouldn't go through. So what would I need to know to actually prove that? To prove that A is sorted afterwards, I would need to know that the element I'm appending on the end belongs in that position. And again, I can say that using the functions that I've already written. I can say that if the last element in the original list is, which way around did I say it? Ascending or descending order? I can't remember. I think it was this way around. Is less than or equal to 100. Well, I'll find out whether I got it right now. Yeah, I said ascending order. Okay. Okay, and now this verifies too. Cool. Are there any questions about this? Otherwise, I'll go back to slides.
Can you hear me? Can I ask a question?
I can hear you.
Great. Why didn't you have to fold and unfold sorted here?
Great question. Can I sort of indirectly answer it during my slides? Would that be okay? I mean, the short answer is sure. we generate all of those annotations ourselves. So you do have to fold. So we build this. Okay, we turn this into a Viper program in the end. So all the problems that I showed you at the beginning of the talk arise, and we solve them all as part of the tool. So we generate a Viper program which is fully annotated with all of the annotations that Viper requires to make the proof go through automatically. That's the short answer. I think I have a slightly longer answer, but maybe not that much longer, to be honest. Thanks for the question. Any more while I'm still in the editor? Okay. So I've shown you what this might look like, and indeed, this is what it looks like right now. So we have this tool called Proceedings. If anyone wants to ask the question as to why it's called Proceedings, I'd be happy to answer that at the end. So Proceedings sits and does this Rust verification work for us. We feed in a Rust program, and it's really a Rust program, but with some additional specifications that are written as annotations. And then we generate a Viper program under the hood. And indeed, this Viper program needs some annotation, which we also generate. And then we can feed back error messages to the user. And these, again, come back at the kind of level of abstraction of the Rust program. So, of course, we report errors with respect to the Rust code, not with respect to the Viper code, for example. So you can read more about this in the paper last year, or take a look at the website. I'll have the link towards the end as well. So the basic idea behind what we're doing in Proceedings is we're taking this type system, which was defined elsewhere, right? It was defined by the Rust language developers. And we're generating from that a set of predicates and kind of corresponding ownership-like assertions that we can use in a technique like separation logic. And what Viper uses is a slightly different logic, but closely related, to prescribe the ownership and in particular give us framing information for free. And then we take things like signatures of functions and we use those to generate pre and post conditions for this kind of core proof. So the part that only talks about ownership, the part that talks about predicates and accessibility and this kind of thing on the heap. And then we use the compiler analyses which are already there. So we jump in and rip out all kinds of information that is present in static analysis that the Rust compiler does, basically to figure out these auxiliary annotations, again, to come back to the question. So we'll use the way that Rust figured out how to type check the program to explain to Viper where to fold and unfold the predicates. Some of that work has to be done by ourselves to sort of augment the information we get from the compiler, in particular because the data structures in the compiler don't always record all the information we would like. And then you can write user specification on top if you want to. And then those are generated as functional specifications and kind of coupled with these core pre and post conditions at the Viper level. And so the idea is this can be usable now by non-experts, at least in the sense that they don't need to be able to write things like the predicate definitions themselves. So they can focus on the properties of interest, which can be 0. You can verify programs with no annotation at all. You can go for weaker properties, like we avoid overflows, we avoid going out of bounds, or you can go to full functional specification if you like. So now if you remember my concern about how much work is involved in developing even these core proofs, well, essentially all of that work is now done by the tool itself. So the predicates and the annotations required to manipulate this ownership part of the proof is all done automatically. And so the users write optionally whatever functional specifications they want, and in particular the baseline is more or less 0. And they work at this abstraction level, which is really Rust expressions ++. We add a few things to the specification language, things like quantifiers, for example, if you want them. But generally speaking, Rust expressions make up the vast majority of the specifications that one writes. To give you just a slightly more concrete flavor of what's going on behind the scenes, if you take something like this struct type that I had in my Rust program, we essentially use this to read off a list definition. So the list is composed of, well, there's a self-reference, which has a val field and an x field, and those are both fields that we have exclusive access to, at least if we have exclusive access to the list. And then there are values at those two locations, and basically every value in the Rust program gets translated as another kind of predicate, which describes the ownership of the right part of the heap. And you'll see this option box list on the right-hand side. So we currently monomorphize the polymorphic types. So option box list is really generated since there was an option box list in the program. We do something a bit more fiddly for types where the parameters haven't been instantiated, which you're welcome to ask about. And then in terms of signature encoding, well, basically the client code that I wrote before describes indirectly via the Rust type system, once you know how the Rust type system works, this kind of property, that there are two lists and they're disjoint in memory kind of all the way down. And so we use this to read off appropriate signatures at the Viper level, essentially, for the corresponding client code. And in particular, if you want to then equip additional functional specifications, these just get stuck on here, essentially. I mean, I make it sound as though it's almost syntactic. There's a bit more work to do, quite a lot more work to do to make everything automatic, but that's essentially the conceptual idea. You get to write whatever you want to kind of conjoin on at this level. Things get a bit trickier in the language as a whole, and indeed we're still at early stages in terms of supporting the general Rust language. But I just thought I'd mention one of the particularly interesting challenges, which is reborrowing in Rust. So Rust has this idea that you can pass in a mutable reference and get out a mutable reference, but you should never have two mutable references to what's basically the same part of the heap. And of course, in functions that do this, you might think that you end up with that as a caller. But the way Rust handles this is that the original reference, could be to a list, for example, is kind of, so part of that list may be passed out in the return value. And from the caller's perspective, what will then happen is that the original reference is frozen and inaccessible until you finish working with the return reference. So you can work with this return reference, and then at some point it expires, and then conceptually that ownership goes back to the original reference. This is all dealt with in the Rust type system itself. And this creates us a few problems for the verification. One is we have to now describe permissions to kind of data structures with holes in a certain sense to explain to Viper what's going on. Another is how do you write the functional specifications for these kinds of functions without exposing the internals of the data structure or somehow counting paths through the trees and this kind of thing. You want to somehow say, well, what is the combined effect after I've done a bit of extra work using this returned reference? So at the Viper level, we use a separation logic feature called the magic wand, which we also have support for in Viper to describe these kind of data structures with holes. If anyone would like to discuss that offline, I'm happy to explain it. For the functional specification, which is of course the part that the user sees, then we have this novel specification construct called pledges. And pledges give you a way of writing a postcondition on functions like this from nth one that talks about how things are guaranteed to look in the future. So here is an example of a pledge, and you see these two keywords which are not Rust, after expiry and before expiry. We're still playing with the syntax a bit. That after expiry essentially says, by the time the returned reference expires, so it's not live anymore, and you've given the ownership back to R, so R is now something you can talk about, the lengths will be the same, and the nth element of R will be the 0th element of the reference that was returned, something like this. These are the kinds of properties that you can write down. So you can in particular say something about the future, say what will be true when this reborrow expires, and you can do it in terms of what the client code does with it, in terms of what the client decides to assign using the returned reference in the meantime. So this gives the callee the full freedom to do what they want with the returned reference, and they don't necessarily need to know the internals of the struct in order to be able to, say, call other functions on the struct to make those changes. And ultimately, this leads to more complicated instances of these magic wand proofs at the Viper level, but again, we annotate everything automatically. Okay, I'm almost there. So we have an evaluation in the original Uppsala paper, so you're welcome to check it out in a bit more detail, but just to give you an idea, we downloaded the 500 most popular Rust crates, and here we ran Proceedings with no specifications, and we switched off the optional checks that the program doesn't crash. So we're basically just reconstructing the, if you like, the memory safety part of the proof. This is more or less a stress test, if you like, for our encoding. And then because we don't support all of Rust yet, we filtered these crates, and in the end we could keep hold of 21% of the functions. So this is a number, of course, we hope to grow in the future. So it's about 40,000 lines of code that we ran. And in all of these functions, every single one, the core proof verifies in Viper. So we generate the analogous proof with all of the annotations in place, and everything works. This is roughly 1 million lines of Viper code, and about 10% of that is these annotations that one would typically have to write by hand. Then to test that we could actually do something in terms of specifications, we added specifications to examples that we found on this very nice Rosetta Code website. So we took a bunch of kind of well-known programming patterns and added specifications of different kinds. So this is just a kind of summary table to give you the kind of order of magnitude. These are relatively small but challenging programs, and they have a handful of functions each. You'll recognize some of the names, I'm sure. And the specification required varied. It depended a lot on what the program was doing and what we needed to add in order to be able to kind of get started with the specification we wanted. They all verified. They verify in different times. One or two of them are like 2 minutes, which is a bit too long, but I think this is something we can work on. This is all with a first prototype of the tool. And what we verified was different. So in some cases, in the first part, we just verified no panics, no overflows. In the second part, we tried for more interesting functional specifications of various kinds. Again, you can take a look at the paper, but maybe just to compare two instances. So if you take the binary search example and just want to verify no panics and no overflows, you'd write 2 lines of specification to do this. If you want to verify that binary search actually gives you the right result, then this takes a lot more specification. On the other hand, it turns out we found a bug. So the binary search example there didn't actually return you the searched for element if it was the very last one in the array. So that's kind of nice. You can take a look at the paper for details of the Viper encoding and how we do this automation, or you can ask me, of course. And there's more information about this pledges construct and which subset of Rust we support, although that's changed somewhat since then. And there's a lot more to come, and a lot more that we're working on right now or hoping to work on in the future. Support for traits and closures, more interesting constraints on these lifetimes for reborrows in Rust. We're working on allowing separate library specifications, which is kind of important in practice. We need support for mathematical types in the end for some of these specifications, and we're looking into supporting some of the concurrency libraries that are commonly used in Rust. And eventually we're going to go to verifying at least some kinds of unsafe code, but ask me about that if you're interested. So I will wrap up. In conclusion, what have I shown you? Well, there's this Proceedings project already. You can check it out on the website, or we have a Zulip chat now if you'd like to ask questions. This dramatically simplifies the problem of Rust verification compared to, say, analogous languages such as C and C++. And we hope enables verification by at least interested and somewhat expert developers. It's developed on top of this open source multi-purpose verification platform. So this is at least the democratizing verification angle. And we generate all of the annotations that that platform requires automatically. And I am looking for master's and PhD students, having recently moved to UBC. So if you're interested or know anyone who's interested, then feel free to get in touch. Thank you very much. I'd be happy to have questions.
Let's thank Alex.
Thanks. I'm very slow on unmute.
So it looks like Mitesh has a question. Mitesh, would you like to ask that directly? I'm not hearing Mitesh. He's asking in Skype, in Slack, what is the difference between correct result, computation, behavior?
Aha. In the table, I guess this is. What's the difference between correct result and correct computation? That is a good question, and to be honest, I'm not sure I remember anymore. Correct computation. No, I'd have to check. My assumption is that this is sort of spuriously different. I don't think it means anything substantial. I hadn't even noticed, to be honest. I don't think there's anything particularly fishy lurking there. Maybe the reason. No, okay, I'm sorry. I don't know the answer. I would have to check. But I believe we verified the kind of the functional specification bit of the problem at least. Sorry that I don't have a better answer than that.
No worries. Looks like Bernhard Kagel has a question.
Yeah, hi. So thanks for the nice talk and demo. So I'm kind of wondering about, you were saying that there are some limitations and there's a fragment of Rust that you support. And I'm kind of wondering if, for example, let's say some more advanced concurrent data structures with sharing, if they can be expressed in the fragment that you have. And also, if you think of that, that some of your automatically inferred annotations and so on, if they are somehow not enough, do you have a way or connection to basically interface down to Viper and add more annotations that might be necessary on the Prousty level, or do you basically want to completely avoid giving any additional annotations?
Mm-hmm. Okay, thanks. Yeah, two very interesting questions. So in terms of the libraries, so let's see. So if you have a concurrent or a trickier library that sort of rolls its own story with respect to aliasing, there are kind of two cases. So one is that you nonetheless expose a safe interface from the point of view of Rust to the clients. So safe meaning all of the functions are not labeled as unsafe. What that means is the clients can treat the type signatures pretty much as any other function in the sense of the ownership story that they provide. What one has to be a bit careful of is right now, the way we treat pure functions, we kind of have this, we treat them as referentially transparent, essentially. So if as long as you have a shared reference to any bit of data, everything you can transitively reach in our Viper encoding is kind of assumed to be immutable while you hold on to the shared reference. So you can make this trivially sound by just kind of breaking the connection inside the library. You don't give the ownership to everything inside all the time, but to then restore some kind of useful framing information for free requires something extra. Then you need to be able to say something about what is guaranteed in between calls to this particular library. So we're working on how to make these kind of safe abstractions of unsafe libraries, how to write those specifications in a way that sort of still plugs back in. But it's surprisingly tricky. It's interesting that even, as I say, if you have this safe API, then you sort of observe some differences. You observe essentially that the library could not be implemented in purely safe Rust. So we're working on what that means at the specification layer. And in terms of the annotations, it depends. So I'm pretty sure we will want things like ghost code eventually. We will want things like mathematical types. So in a sense, this is all something that will get pushed down to the Viper level, but nonetheless, you'll work with it at the Prousty level. Nonetheless, I hope we don't go to that level of abstraction in a sense. I think what's really nice about the project so far is that we managed to present information and an interface to the user, if you like, which is pretty close to Rust, pretty close to the way one writes things in the programming language itself. And I'd very much like to keep things that way as much as possible.
Yeah, I mean, I definitely agree. It's just that basically it could be very frustrating for users if they at some point they just hit a wall and there's no way to somehow even with more manual work get the verification done.
Yeah, I totally agree. So we work very hard in Viper to make the annotation requirements very predictable, and in that sense, since we take care of generating those annotations, at least for things like the predicates, you can hide the fact that these predicates even exist from the user. This is the kind of thing we hope for. If you start weaving in more and more quantifiers to the specifications, at some point you get into the SMT issues to do with e-matching and matching loops. I suspect ultimately we will have to lift things like triggers to the Prousty level. So patterns for matching these quantifiers. At least I don't have a good alternative right now. So I mean, many of these functions in this table and also some others we've written do use quantifiers. We managed fine for quite a bunch of programs, but essentially because we sort of know what we're doing, if you like. We know ways of writing those quantifiers that work better than others, I suppose. And for simple problems, the issues don't arise as quickly as one might think. But at some point, that's going to be an issue. And I think for patterns, for triggers, whichever you call them, I mean, I don't know of any good solution that maintains purely this level of abstraction. But again, at least the quantifiers will be written at the Rust level. I guess the pattern syntax will also be some kind of Prousty level annotation. And so to an extent, one can still explain the feature at that level. I think we don't need to expose anything from SMTlib or from Viper or something like this. That's the kind of place where I expect we will need our own annotations. That and kind of ghost reasoning. But ghost reasoning is, again, kind of at the level of the programming language, if you like.
Okay. And just one last small question. At least I hope so. Is this
Sure.
this pure annotation you had in your examples? Like what do you have to check for pure like I don't know if it's a predicate or function? Like do you, for example, have to check somehow termination?
Yes, but we don't yet. So we just added a feature to Viper actually to make the termination checks much easier to generate. So we'll probably do that soon. So the property, I mean, in the end, it just has to be some well-defined mathematical function. So in theory, of course, termination is also an over-approximation, if you like, of what you really need. But I think in terms of actual executable Rust code, it's pretty much what you want. So leaving the ghost story aside, I'm pretty sure termination is something you want. But you need, of course, that there are no side effects. No non-determinism. The way this is enforced at the moment is essentially syntactically. So there's just a limited fragment of Rust, I mean, an even more limited a fragment of Rust that we support as a pure function. And if you go outside that fragment, you get an error message. At least I hope you get an error message rather than a crash. And it will say, you can't do this in pure functions yet. So right now, you have no facility to generate side effects just because we don't support any features that you could use to generate side effects. So at least some of the issues go away by construction, if you like, just because of the fragment that's allowed there so far.
Okay, cool. Thanks.
No problem. Thank you.
Alex?
Hi.
Go ahead, Ari.
Alex, can you comment, like on the slide, can you comment on the times? Like,
Sure.
Are they reasonable? Are they much higher than expected? They're in line with what one gets with other tools on other languages? Or?
Yeah, I think they're a bit slow. So if you compare to what you can do by hand in Viper, they're quite a bit slower. I mean, one trivial answer to that is just that this was the first version of everything. So I'm sure we can optimize many things. Another engineering issue is that all of the interaction with Viper is done via some native interface in the end, and some of those calls take time. But I still don't fully understand, to be honest, why some of the examples get as much slower. So for example, I would expect, given my experience writing these kinds of things in Viper by hand, I would expect numbers more like up to 10 seconds for the vast majority of examples, and then maybe there'd be one or two where you go to like 30 to 60 seconds. So with that in, again, if you have a lot of quantifiers, you have a relatively rich functional specification. So it turns out, for example, this Knights Tour example, which is slow even when you don't add the functional spec, you kind of need to almost write the functional spec anyway, just because of all of the properties you need in order to prove that this doesn't go outside the bounds of the various arrays. Mm-hmm. So there's a lot of specification there, basically, to cover why this code is really safe, why this code doesn't ever crash. It's relatively complex invariance. But even so, I would kind of hope one could do that in 30 seconds to a minute. So we'll see. We're looking into some engineering aspects of just making the tool faster in kind of not methodological ways, but the way we interact with Prousty, the way Prousty interacts with JVM, these kinds of things can be optimized. But I think the encoding itself to Viper could also be optimized further. I think it's hard because we're dealing with generated Rust code as well. We take some intermediate representation from the Rust compiler, so the code is also much, much longer. And the technique we're currently using is essentially symbolic execution in Viper. And because you get a lot of kind of bonus branches in the generated code from Rust, then that could be a reason why things get much slower than kind of working at the source code level. Yeah, but it's definitely something we'd like to improve. We'd like to make it a lot more responsive for more examples. I think for some of these examples, it's, from my perspective, okay. I think anything under 10 seconds is kind of fine in terms of this sort of interactive development. It would be nice to make it more like 3 seconds, but we'll see.
But is the interaction mode similar to Daphne and tools like that? Because like in that mode, 10 seconds is a lifetime.
Yeah, but it happens.
Right, but
and it happens for the same kinds of examples where you have lots of quantifiers in the invariants.
Right, but
yeah, I don't know.
Like
I think
search 20 seconds. I've done binary search in other tools, so it doesn't take 20 seconds. Right, like I understand
I agree.
Saying that, but this binary search, because the way it's described, it involves lots of difficult things.
Yeah, because it's a real implementation from a library, I think. Well, maybe not actually. Maybe this one is. Well, in any case, it's the compiler generated version of the code, I suppose, is the reason why the code is not so nice. I think it's a fair point. I don't think 20 seconds is what we're kind of aiming for.
So you're saying that like the compiler could just verifying small snippets of code just because it's compiler generated makes it a lot harder?
Yeah, because they're not small snippets anymore. The generated code is many times longer with many more auxiliary variables and branches that don't exist in the original. So it's, I mean, at least an order of magnitude longer in many cases. But
like I'm wondering about it also from perspective of our experience with Seahorn and Smack, because we had then, so for example, Smack is maybe closest to something that can be compared because it also uses Boogie, but it works off generated code, as opposed to say Boogie that you produce from Daphne. Right, then I see. Like I didn't think how much extra time would be just in that somehow it's expressed less clearly, and
but it's
I guess
also
you have
doing
to rely more on SMT solver to actually do more of the search.
Right, but it's also doing bounded verification, right? So you don't need
invariants,
I guess.
So are you. Like the verification that you actually do the time, that's all bounded. Right? You're checking whether something is an inductive invariant. You're doing lots of bounded checks.
Yeah, sorry, I mean bounded in the sense that we explore, if you like, all executions of the program.
Right, but same with Smack and so.
Then maybe that's my misunderstanding, but my understanding was you don't typically have to write the inductive invariants there, but then by default you do.
Well, but you can, and then the tool will check that they're inductive. I mean,
okay,
yeah,
well, it would be very interesting. It would be very interesting to take the same example then, and I mean, we have the invariants, so you could try them in the tool.
Right.
It would be nice to see.
Right, like the targets are very different, and how the tool is supposed to be used are very different. But once you boil it down to saying like, well, if I have this code nicely written, and then if I take this code through a compiler and then I re-encode it, and that makes a big difference to the SMT solver, then in that space, what the tools do are very, very similar.
I mean, one big difference that comes to mind, though, is like all the stuff that they're doing to encode heap props just by default, right?
Yep.
Mac, for instance,
I should. Right, absolutely. It's not similar at all. I agree. Once you get to any level of detail, it's not similar at all.
Yeah, I guess you get
absolutely.
frame conditions, if you like, for free this way. And in that sense, if you want a specification that scales up to, say, calling binary search on arrays of arrays and nonetheless knowing the same level of detail, I mean, I can't claim that I know the time that would be involved, but those frame properties turn out to be almost as essential as the functional specifications. And as annoying to write, if you like, and certainly involving many quantifiers. So here we get frame properties for free for all of the heap that the Rust type system does not let you modify. For the part of the heap that, according to the type signature, you are allowed to make changes to, then you have the usual story, if you like. You write the same kinds of invariants. I think that's probably a big difference if you want to scale this up to callers and callers of callers.
So do you think there is some potentially missing SMT theories that could help? Like potentially you encoding with quantifiers some decision procedure that could be implemented directly? Like just because the language is so rich and you can express a lot of things, you may end up doing that rather than, say, creating an algorithm.
Yeah, it's an interesting question. I think it depends how rich the functional specs get. So in some cases, you want things like comprehensions. So you want to say things like the sum of the elements, the count of this many elements. You want to do things like filters and counts in the specifications. This we end up encoding with lots of quantifiers in this kind of verification typically.
Right, but I'm looking at the first part of your table. Right, the first part, there's no panic, no overflow. I'd imagine there would be much less of that.
Yes, that's true.
Right, like you made one exception, like something.
I think for the Knights tour, that the problem is, as I say, that you end up more or less having to describe the functional spec of what a Knights tour is.
Mm-hmm.
I wouldn't know how to pick a good theory. That seems very sort of specialized in a certain sense. But for the sorting algorithms, yeah, it's mostly, of course, I mean, what you need to know you stay within bounds and this kind of thing. I can't think of a theory offhand that would help so much. I mean, there are sequence theories, of course, but my experience using the sequence theories at the SMT level is that the performance is much worse when you combine them with everything else than writing these things by quantifiers by hand. So you could, I mean, that would be an alternative specification you could write, but we didn't have much success with that in Viper so far. We tried that on quite a few examples.
Right, but it's an ongoing thing, so.
Yeah, I have the feeling, but I might be wrong, I have the feeling those theories work much better if you're interested in the SAT cases. And then, of course, the quantifiers approach is not that much use. And I have the impression the theories also perform better in those cases, but I might be wrong. In the Unsat case, like I say, at least when you mix them with enough other stuff, including user-defined quantifiers, which I think are sort of unavoidable to an extent, then we didn't have much success.
Right.
So we do a lot with quantifiers by hand, also in Viper itself. So Viper, when it maps the verification conditions down to SMT, generates lots of its own quantifiers. But we do this in some way that we generate the e-matching triggers very carefully, so that, again, we anticipate
that's why I'm
instantiations will be.
It, as a decision procedure, right? Like there have even been papers that showing if you control e-matching, then you can generate your own decision procedures just that way. But they're not necessarily most efficient.
Yeah.
Like complexity-wise, they could be quite efficient, but once you go to raw time, then you can.
I think what would help us the most at the SMT level is if there were a more efficient way of encoding the branching that the symbolic execution does without essentially redoing a whole bunch of the quantifier instantiations. So typically you end up hitting proof obligations with many overlaps, if you like. Many proof obligations have relatively similar goals, but because of the way, at least we use the push pop mechanism in C3, I think. Mm-hmm. Because of the way that works, if you roll back, well, I mean, this is probably a longer discussion we could have offline, but if you roll back an obligation that caused many quantifier instantiations, it could nonetheless very easily be that in the other branch, you do them all again. This relatively easily happens, and there doesn't seem to be an easy way to remember parts of what C3 deduced in the previous push pop block. my assumption is that this is where we lose a lot of performance. It's also my experience in Viper itself that the symbolic execution verifier, which we use, gets a lot slower if we use quantifiers in certain ways. Whereas the boogie-based verifier, which we're not currently using in this Prusty project for other reasons that I'm happy to discuss offline, is much faster in some of those cases. And so this could also be why we suffer in some of these programs that use a lot of quantifiers in the end in their specifications.
I think Adad wants to add something to the discussion.
Okay.
Yeah, thanks. I wanted to ask another kind of higher level question.
Okay.
So first, do you have a completeness result that says that if the Rust compiler says that the program is fine, it means it was able to prove, I guess, that it didn't have some class of problems related to ownership and data races, then the Viper that you automatically generate with the automatically generated folds and unfolds would at least prove the same thing that the Rust compiler proved?
Interesting. I mean, it would be very nice. There's no such formal result. I mean, it's not quite clear what one would connect to at the Rust side. There's no formal specification of the language or the type checker or the borrow checker. So I guess what we do is nonetheless model what the compiler is doing, in a sense.
Have you run into an example of a program where the compiler was able to convince itself that you don't have a data race or that the ownership is preserved, but in the Viper you actually had to do something manual to get to say the same, to be convinced of the same thing?
No, so that's basically what we show in this first evaluation, is that for at least for the fragment of Rust that we support so far, which I mean it's still smallish but will grow over time, that never happens. And I mean, of course, it can happen due to bugs in Pusty in theory, and I'm sure we fixed such bugs basically by running such an evaluation and then realizing something's not right. But it's not that we're doing anything heuristic in generating those annotations per se. There's no kind of, well, I guess heuristic is the word. There's no heuristic there. In principle, we're doing something that always works. In practice, it may not work because of bugs in our implementation or our understanding, but then we fix them. And I hope that will remain the case as we grow the subset of Rust as well. Because what we try to do is reflect why the Rust compiler accepted the program, if you like, but in a logical sense.
And another question, what's the largest project that you've tried or that exists that uses Prusty for functional verification? So not just memory safety, but
It's probably still essentially individual functions for the moment. So we're working with some data structure verification problems from Amazon Web Services. So there, well, we have let's say sort of toy versions of the real software with clients and this kind of thing. But I think we're just kind of getting started on these actual case studies now, basically. So on using it for something more serious. I would guess the largest, at least where we're showing something interesting in terms of a functional specification, are things like sorting algorithms. But these are, yeah, this is probably, as far as it goes, where I could claim that we have a rich functional spec that we're using. But I think that's going to change in the next few months. I think we'll have a lot more. We need a lot more features in practice. If you apply this to the kind of real code and you want to, want to take a whole project or even a reasonable chunk of a project, you just hit lots of features at the moment that we don't support yet in the tool. So there's a lot, you always use closures in one way or another. You use traits pretty much all the time. There's a lot of standard libraries that we need to equip with specifications. And right now we have to wrap them all by hand, which is very tedious and time consuming. So we're kind of working on, well, those three things right now. And once those are much easier to use in the tool, I think it will be quite easy to sort of roll it out to much bigger code. And then we'll probably hit the next set of problems, but that's okay.
Thank you.
Yeah, no problem. Thanks for the questions.
Any other questions for Alex.
Hey, Alex, this is Sid.
Hey, Sid.
I have a sort of maybe a silly question. Is there a way to sort of turn off Viper checking the things that the Rust type system is anyway checking for us, and then just check the functional stuff that you layer on top? That might help with the timing issue, for example.
Yeah, it's an interesting question. In a sense, if you trust the compiler, which we sort of do, I guess, then what we're doing is a bit redundant there, because Viper will indeed check that you have access to the heap, even though the compiler has sort of checked that already.
Yeah, exactly.
I think that the difficulty is you can't really abstract that part of the proof away from what Viper knows, because it needs it for framing, right? That's the big advantage to the whole methodology, is that you get all of these frame conditions for free without having to write any specifications. So you need the permissions part of the story at the Viper level. I don't think there's again, it's a bit technical in terms of how the verifier is implemented. So I don't think the symbolic execution tool can avoid, in a sense, looking up where on the heap those locations are, which is effectively the permissions check. You could tell it as a free assumption that it's somewhere on the heap, but it turns out encoding those free assumptions is not so much cheaper in terms of the SMT queries that it ends up generating, I think. Ultimately, if you tell it you've got this permission somewhere, to make use of that fact, it still needs to run over all of the chunks in its symbolic state and figure out where that's meaningful in a certain sense. I think if we had support for the boogie-based verifier, that would be much more beneficial. And the reason we don't do that yet is the boogie-based verifier doesn't scale too well to having huge numbers of predicate instances. And we're also looking into maybe a different encoding there. But the way these generated Viper files turn out from Prousty, you have many, many predicates and many instances of the same predicate, and that turns out not to play so nicely with our boogie encoding. So I think if we could fix those slightly orthogonal problems, then in the boogie version of the program, or in that verifier, adding these assumptions to basically say, don't even bother checking that you have permission, this is much easier. Because the representation of the heap is ultimately just one big map in the boogie representation, whereas in the symbolic execution tool, you have this information about the heap distributed across the chunks in the symbolic state.
Yeah, I see. Yeah, that makes sense. Thanks.
Yeah, thanks for the question. It would be cool. I mean, we do, of course, mildly benefit, at least while we're developing the tool, just from the fact that we catch our own bugs if there's something wrong in the encoding. You know, Viper will also complain, not only if the Rust compiler were wrong would Viper complain, but I guess if we were wrong in mapping what the Rust compiler did, then Viper will complain. But yeah, it would still be a nice thing to be able to switch on.
Cool. Any more questions?
Hi, Alex. This is Thomas. I have a quick question.
Thomas.
Did you find any bugs in the Rust compiler in the type checker?
No. No, it would be nice. Now, like I say, we did find bugs, I think, in a couple of these examples that we applied the tool to, these Rosetta code examples, which are, I mean, just teaching examples, I guess, in the end, but still. No, we didn't find anywhere where the Rust compiler was wrong so far. Maybe that's because the subset we support doesn't have the really hairy stuff in there, or maybe it's because the bugs get found very fast at the moment. Yeah, it's hard to say. So we're adding support for much more complicated lifetime constraints in function signatures. And maybe once we have that, then we'll find some cases. I don't know. But yeah, not so far. I think the compiler is, well, the code is tricky to understand, but it seems to nonetheless work most of the time. So whether that counts as being in a good state, you can argue, I guess. It certainly seems to be in a good state in some respects. It's quite impressive, really.
Okay, thanks.
Okay. Is that it for questions? Seems like it. Okay, well, yeah, on behalf of Democratizing Software Verification, we want to thank you, Ari, Jorge. I are very, very thankful for your participation, speakers and audience both. Just a couple of things for everyone. Please, contact us, send us feedback, what you liked about the workshop, what you didn't like, what worked and work. Specifically for speakers, we have this Slack channel, and people have still asked a couple of questions. Questions might be ongoing. It would be great if you could monitor and respond to those questions as soon as you can. It's much better that these questions and answers get broadcasted in public rather than in private, so everyone else can see the answers to them. Furthermore, for the speakers, well, for the audience and everyone, like I said, this talk is recording. We're going to probably put it on YouTube. We're still working out whether it's going to be individual videos or one long sequence. But for the speakers, please let us know if you specifically do not want your recording on YouTube. Otherwise, we'll just assume that you're okay with it and we'll do it. Yeah, so once again, thanks everyone. From our perspective, this looked like a pretty nice success, and I really enjoyed listening to the talks. Thank you.
Thanks to the organizers as well.
Thanks a lot.
Yes.
Thanks, everyone.
And yeah, like I said, let us know your feedback. Hopefully we'll be back next year with a possibly live edition of the workshop.
Well, this was live. It was live and synchronous.
Yeah.
Yeah, I have to say, surprisingly, this went quite well. We had some technical issues, but that was fine. And at least I find the talks are very engaging. I was worried that since it's just sitting here and staring at the computer, at some point you start falling asleep, but I think it went quite well. Thank you all.
Thanks, guys.
Thank you, guys.
See you next time.
Thanks.
So you're gonna stop the recording now?
Well, let's press stop. Stop.